for our safety minute. So summer driving. So we're getting into the summer here. There's a lot of kids out of school, teen drivers out there, a lot of people out enjoying themselves, doing things like that. So we just want to be aware. So take that extra time, look twice, look 3 times, before you pull out, so that you don't have to, end up, dealing with an accident or yourself. Also, the heat, affects your car's performance. Make sure that you have water. If you're ever, if you're going to be in an isolated area, you want to make sure you have water and things like that, so that if you do break down or have a blowout or something like that, that you're safe and protected. So so that's kind of our safety minute, and with 9:05, that is my time, so I'm going to stay on schedule here. But again, thank you all for coming, and we're going to get right into it with the first presentation, which will be Soumya Balusu and Shashank Patel. Soumya.
Hey, good morning, everyone. I'm going to share my screen. All right, I assume everyone can see my screen. Good morning, everyone. I'm Soumya Balusu with SCS Engineers, and along with my colleague here, Shashank, we'll be talking to you about landfill closure. So a little brief intro for me and Shashank. I'll let him go here in a second. I've been with SCS for about 6 years, and I've been in the solid waste industry for close to 18 years. And a little fun fact about me is I practice the other side of my brain, separate from engineering. I've practiced Indian classical dance and performed since the age of 7. I'll let Shashank go here with a little introduction, and I take back over.
Hey, good morning, everyone. I'm Shashank. I work out of the Atlanta office for SCS. I've been here for 5 years, 6+ years in solid waste. And a little fun fact, I play soccer. I coach soccer since past 2 years, and shout out to any Arsenal fans out there.
All right. So going over our agenda here, what we'll be talking about, I'll be doing the first couple of slides, and Shashank's going to do the bulk of the presentation here. We'll go over closure, what's an overview, what triggers it, what are typical types of capping systems, and then we'll talk about what to plan for when you're designing a closure, some considerations for leachate landfill gas as you prep for closure. Think about construction and bidding, material costs that are all over the place these days, and of course, plan for contingencies. And then kind of wrap it all up in our conclusion slide in terms of the takeaways for the preparations for closure. So what triggers closure? It's kind of different in different states. It could be that you got your final load of waste and you are undergoing a full final closure of your landfill, and you're typically required in Georgia, you're required to notify the director of the regulatory agency within 30 days of receiving the final load of waste, and then that triggers your closure process. Another trigger typically is what's in your permit in terms of the maximum open area that you can leave without performing closure. So that's typically tied to your financial assurance mechanism and what you're putting away for closure, post-closure. So that's something to look at as well. And here we have a typical phasing closure sequencing plan that we did to prep for that maximum open area that I was talking about. So in terms of different types of closure systems, there's a lot out there, right? What we're all familiar with is the traditional final cover system, which is the subtitle D closure system that you can see here on the left, right? It typically has your intermediate cover that serves as that liner subgrade. You may have a low permeability material below your synthetic liner, the synthetic liner material, a drainage geocomposite, and then protective and vegetative soils on top in order to sustain vegetation and stabilize the site. Obviously, in the last few years, we've seen a lot of other systems be permitted, both for temporary as well as in several states, a final cover system with a financial mechanism in place for replacement during the post-closure period. And that's the exposed geomembrane final cover that we've started to see that quite a bit. It's straight up exposed, and it has the option for solar panel installation on top. And there's that. And we're several of us are aware of the synthetic turf, closure turf type material that can be used with a ballast material on top for closure as well, alternate detail. So with this, I will pass it on to Shashank, and he'll start talking to you about what to plan for, starting with as you're completing the design.
Thanks, Amya. So, when we get into a closure design planning, the theme of this presentation is going to be planning. So you have the preparedness before you go into the construction phase. So before you get into closure design, you need to identify where your tie-in locations are. Like, is your anchor trench truly following what your closure design or a conceptual closure design is following? And confirm your soil thickness. There will be, the intermediate soil cover or the layer before you put the liner down. So you need to go back and confirm that you are meeting your permit requirements before you put any geosynthetics down. And then identify any areas of, fill, cut to make your stormwater design work, and any areas of waste overfill. Now, these could be tackled in multiple ways. One of the options is if you have overfill in certain areas and underfill in certain, then it's a discussion with the state. So again, planning, as I mentioned as a theme, you may want to have that dialogue to understand if the total volume matches up, and if the state would allow you to proceed with the closure if the stormwater design makes sense. Going on, leachate considerations. Being in Southeast, none of us are immune from not having rain. So is this site a wet site? Identify and flag any existing leachate outbreaks. Make a plan of tackling those as part of your closure design. And then address them as part, with multiple options out there, toe drains, French drains, or any vertical sumps that you may have to look into to, incorporate in your design. Stormwater considerations. That's the biggest challenge, with closure. And we'll go more into the rainy season on that. But stormwater consideration, need to look into how much fill will be needed on your benches. Evaluate slope on the benches so the stormwater design will work. And then showing more details to show your stormwater outlets daylighting. And here, I've shown an example of a construction challenge that we faced. On the right is a picture of how a down drain was constructed. And on the left bottom, you can see a detail. The detail calls out for the toe drain, down drain structure to daylight at the berm location. Now, there was not enough definition in the plans, so the contractor went ahead and installed it without thinking it through. And as you can see, the outlet is just laying flat on the bench there. So even after that 12 inches or 18 inches of cover on top, it won't daylight. They were able to make it work, but with extra cost and effort that was required, and engineering assessment on that. Now, landfill gas considerations. You're moving into, closing that hill. What will you need to evaluate in that? What the closure will impact in terms of existing GCCS? If you need to raise your existing wellheads, if you need to add any more wellheads to that, what your final design looks like, how that ties into your either final design or NSPS plan, and if there is any other infrastructure that needs to be added before the closure can be approached. And then considering the phasing of the GCCS construction, if you want to go ahead and get a GCCS contractor in, get that addressed, and then bring a closure contractor so there's no conflict and two parties working in the same area. And then while you have a contractor on site, you may want to evaluate, any aging infrastructure, which is either your flare, compressor, or any other piping associated with your GCCS components. Now, construction and bidding schedule. Here in the Southeast, we get a lot of rain. And with closure, you're fighting stormwater constantly. On the right, we've shown a climate chart for, the Atlanta area, but again, we see similar long drawn rainy seasons throughout the Southeast. So what would make sense is bidding it during the rainy season, planning it during the rainy season so you don't have boots on ground heavy equipment contractors sitting out there and waiting, to ride out the rain event, or reworking the slopes with, the soil washing down. So bidding during rainy season, staging your construction more for the dry season. Typically, we want to, look at a 20-25 acre closure area to avoid interaction with the rainy season. And then, as I mentioned, during rainy season, you can do all these, initial legwork, which is shop drawing reviews, material procurement, conformance testing, and material delivery. Material cost. Obviously, you're looking into closure. Cost is going to be the bigger driver here. Costs are ever so changing. Material prices are rising each day. Geosynthetics have, gone up by anywhere between 100 to 300% in the last year or so. So a few things to evaluate in this situation. If you have enough time and, on hand, if the owner, either it's the county or the private owner, they want to, look into buying the material, what it would do is save you a 15 to 20% markup, which the contractor typically has. But if you're looking into that, then you invite this added responsibility on the owner side, which is getting the material, unloading it, storing it in the right location. Geomembrane stores outside pretty well with some cover on it, but you may want to look into some storage for geotextile, GCL, which is susceptible to moisture and UV. And then strategies for low bids. More definition in plans will always help. Having more defined design with more details, with more call outs, having exact locations either drawn out or, just a tabular form of where you want your stormwater features or anything that specifically needs attention and doesn't need to be figured out while in construction mode, because at that point it will be too fast paced. Chances of failure are significant in those situations. More breakdown in your bid forms. Again, we don't want, 1,000 line item bid form, but again, breaking it down will allow that risk to be mitigated. And then a contractor pre-qualification. While we're going through this design phase and all that, you can work with the purchasing and start pre-qualifying your contractor, so you don't have to worry about who you're dealing with while the bids come in. Now, planning for contingencies. You can plan everything, but there will always be contingencies during these big major construction events, leachate outbreaks being one of them. With soil moving in, heavy equipment moving around, and waste consolidation, there will be spots where you'll have either wet spots or leachate outbreaks. So having extra details in there if there are any issues like that. Raising your GCCS components. Soil will be moved in before and after the liner, so you have like multiple events where the stub up will be at multiple heights. And if you have an ongoing monitoring schedule, then you have to evaluate that to maintain your compliance requirements as well as to keep the contractor moving. And then, impacts of construction on gas quality. Contractors may hit infrastructure here and there, so you have to line up people or either put the onus on the contractor to repair stuff. With that, if you have a beneficial reuse plant, gas quality is one of the priorities for them. So plan for that if there is any construction activity to either isolate the well field or plan accordingly. Moving on, managing liquids. As we mentioned, leachate outbreaks. This is an example of an ongoing closure and leachate outbreak. You can see on the picture on the left, there's a puddle of leachate. In the middle, we have an option of someone, coming in with a vac truck and taking all that out. But in these situations, you'll have to constantly look at these areas and evaluate. If it is a one-time event or if it's a continuous event, then you have to look into a permanent infrastructure to address that. Because once you put the liner down, you won't have the option to go back and fix it, but it'll be an expensive fix at that point. Some of the other options we've looked into here in the pictures, we can see at the toe of the slope for a closure, we see these layers of geocomposite. The intent behind this is the geocomposite will provide a media for any moisture or leachate or liquids to flow down to this low spot. The next slide, we can see, on the left picture, the geocomposite was extended upslope. The reason behind that was they identified a wet spot or a continuous leachate outbreak. So extending that further up just gave the leachate the pathway to flow down to the low spot. And on the picture on the right, you can see the excavator putting a vertical stub up, which can be utilized to put a pneumatic pump or any pumping mechanism to extract liquids and not have liquids accumulate at the toe of the slope. And just some pictures from our lessons learned through an ongoing construction. The contractor was pre-qualified. Everything looked good on paper, but when it came down to extending infrastructure, the contractor felt like it was appropriate for them to raise air and force main HDPE pipes using PVC pipes. So obviously they had to go back and fix that, but things like that can happen when you don't have the right people doing the work for you. And in the right, you can see air release valve in a vault box, and rather than raising the entire component, they just decided to raise the stub up for that with a PVC pipe. So overall, preparations for your closure, like as we went through this presentation, thinking of closure, what can you do right now before you actually go into construction or in a design phase? To look into your tie-in locations, evaluate if you need to come up with what area you're looking for your either a partial or a complete closure. Your GCCS evaluation, evaluating your existing as well as your final needs, managing liquid outbreaks, soil cover depths to confirm that you're meeting your permit requirements. And then talk to regulators. As we mentioned earlier, if you have areas of waste relocation or anything like that, if the regulators are willing to look into a plan, or if not, then what are the other options? And then strategizing with your purchasing. With that, we conclude our presentation.
Looks good.
Thank you. All right. Good morning, everybody. Let's see if we can pull this off earlier than I expected. So this morning we'll present on alternative design to base grading for landfills. And we'll look at an example of a certain, parameter related to that design, and we'll talk about the benefits of using this alternative design to base grades. So to start off, my name is Belinda Ricklin. I have 16 years experience in the solid waste industry, and I've been 6 years with SCS. My hobbies, to present something about myself, I enjoy traveling and hiking, and I'm actually off Sunday on my next travels. So, and I'll let Abdul, my co-presenter, introduce himself.
Good morning, everyone. I'm Abdul Mullah Saleh, and I have about 4 years of experience in solid waste and environmental projects. I have had the opportunity to work at Masdar City in UAE, which is a city designed to be zero waste and carbon neutral project. That was very exciting and a good experience. My hobbies include soccer and swimming. I've been playing soccer with the college and coach some soccer, and lately I'm into swimming now. Thank you.
All right, so let's get started. So I'll present, kind of big picture, what are we talking about here? So on the screen, you see our kind of the typical design for most landfill base grades is the herringbone design, where in this slide you see the sump to the right, which is the small square down here, with the pipe slope rising down the center. And then you also see on this herringbone design that the berm itself also slopes up, to keep the grades with the base. So talking about the green design, here on the left-hand side, you can see the green design, and it's mainly a geometry change on how you do your base grading with the sump as well at the, on the right of this cell for this example. And your sump actually runs down the center of your cell with the base floor sloping towards the sump in a perpendicular fashion. The slope is perpendicular to the sump. And then the berm on this green design is constant elevation. There's no need for the berm to rise in elevation. So that reduces some of your fill for this design. There is no change to your lining system. That design stays the same, whatever planned for that cell. And then your pipe slope is selected, based on your geotechnical evaluation and your settlement analysis. And you can use the same design actually that has been used on the herringbone and apply it to the green design as well. Those same slopes can apply. On the hybrid design shown on the bottom right of the slide is when the cells get much longer inland. So at the sump will end at this point here in the center, and then it switches to a herringbone design. And Abdul will go into that in a little more detail towards the end of his portion of the presentation. So at this point, I'll hand it over to Abdul.
Thank you, Belinda. What I would like to do today really to emphasize on 3 distinct attributes of the green design. The first one, we look at the leachate pipe flow conditions and what kind of condition the leachate flows in the pipe under the 2 scenarios, the herringbone and the green design. Then we look at the sump design. The sump design is different between these 2 scenarios, and we look at the volume that will sump provide, and also that will impact the pumping cycle of the leachate, where we can pump the leachate out of the sump and recharging the sump and see how that will impact the operation and maintenance of the pumps. Finally, we will look at hybrid design. How can we maximize the length of the green cell before we go into hybrid design? We will look at chart that will help us in really look at some analyzing the depths of the sump versus the slope, which will give us some ideas how to maximize the green design of the cell. Pipe flow condition in the green design, the pipe flows under submerged condition, which will provide the flow to be maximum within the pipe dimension 8-inch. Usually we use 8-inch of pipe. In the herringbone design, the flow is strictly flows by gravity, which is provide much less flow capacity than the maximum can be carried out through the pipe. For example, if we have an 8-inch pipe at slope of 0.35%, the maximum flow or the full flow capacity of that pipe is 470 gallons per minute. And where does that come from? If we look at the Disco pipe design manual, which will have, it gives the capacity of the pipe, full flow capacity of the pipe, and based on the slope. The x-axis here is showing us the slope of the pipe, and the y-axis is the dimension, diameter of the pipe. So if we look at 3.5%, roughly slope, 0.35% slope of the pipe, the 8-inch pipe can give us about 470 gallons per minute. Now, this is for water flows. I know we're dealing with leachate, it's different than water. However, this will give us an idea that we have much more capacity in the leachate collection pipe that we can utilize. Now, where is the pipe located under the herringbone design or the green design? In the herringbone design, if you look at this chart, the leachate pipe is laid on a grade 0.35 or 1% or whatever the grade is, and the invert of the pipe sits at the top of the sump. So actually, it will be discharging into the sump by gravity until the sump fills up, then the leachate will be pumped out. In the green design, the leachate collection pipe invert sits at the invert of the sump. That will give us that the sump and the trench that the pipe is located at is becoming like one big or large sump that we can utilize to store the leachate in it. So basically, this is what the difference between the 2 design considerations. Now, it's very important that we have good settlement analysis of the cell that we can design. Geotechnical information and settlement is very critical because when you design for a green cell, you're really depending on the post-settlement grades, because this is what control your grades, as we will see later in the chart, how that will affect that. Okay. Okay, now we look at the some design and the herringbone. Usually the herringbone some design in this scenario is the sump is very much smaller than the green design, and usually sits at the bottom of the cell at the invert, and the capacity usually it is not that large. So for this example, we have a typical capacity of the herringbone design sump about 642 gallons, which is that's situated at the low end of the sump. Now, usually when we have we want to pump the sump, we use either 40, 60, or 80 gallons per minute pumps. For this example, we're going to use 60 gallons per minute. So if we have 642 gallons of sump capacity, we're going to pump it out at a rate of 60 gallons per minute. That will give us 11 minutes of the pumping period when we can get rid of the leachate. Then, based on the impingement rate of 19 gallons per minute that coming into your cell, going through your waste and the liner system going to the sump, the recharge period will be 642 divided by 19, that's 34 minutes. So the total cycle of pumping and recharging the sump will be about 45 minutes. And if we look at that, based on the cycles per day over here, you will have about 11,680 cycles per year for the herringbone design. We have some computer glitches. Okay, here's the green sump design. As we can see here, the sump in the green design, it extends all the way up until the end of the pipe. And the volume of that sump is much larger than the sump provided under herringbone design. And the idea here is the cross section of the sump at the low end will be carried out so can maintain the cross-sectional area. So as we move up with the sump going on the slope, we need to become wider. The sump will become wider to provide the same volume or cross-sectional volume that the pipe is sitting on to provide that adequate volume to be in the submerged condition. Under this example, the sump capacity is about 380 gallons. So it's much, much larger than what we saw in the herringbone design. If we pump it at 60 gallons per minute rate, the time to really evacuate the leachate is going to be 3,800 divided by 6, about 63 minutes. So it's going to take over an hour to pump that leachate out of that large sump. Now, to recharge it, it's going to take basically the same thing. If we have 19 gallons per minute impingement rate, it's going to take 200 minutes to recharge the sump because it's a large sump. So this will give us about 260 minutes per cycle. If we look at that per day and calculate it per year, that's going to give us about 1,998 cycles per year. That's much, much less than what we saw in the herringbone design. Please work. So really, in summary, the herringbone design, the number of the cycles per year that pumps coming on and off is about 11,680. Whereas in the green design, we have much longer cycles because of the volume of the leachate within the sump. So we'll have the cycles per year is much less, which is 1,998. Of course, this is quite a difference between the two scenarios, and this will help in reducing the maintenance cost of the pump and providing longer life for the pump. So actually, this is one of the advantages that you can get from the green design.
Okay, Thomas.
Okay, so this is the fun part now. How can we determine how long our green cell design is going to be? And what are the controlling factor or the parameters that we can evaluate to maximize the length of the cell? So basically, if you look at this chart, we have the depth of the sump on the x-axis, and we have the slope of the pipe or the slope of the sump on the y-axis. As you can see, the lower the slope is, the longer the cell you going to have. So that's why post-settlement grade is very important, because 0.1% centigrade, 0.2% centigrade is going to make a difference under this design. So if we have, for instance, 0.35% slope, and we go on to design a cell 750 feet long, let's say. So if we go there, we know that we want to have a sump about 2.7 feet deep. So that sump will have 2.7 feet deep at 0.35% post-settlement grade will give us a length of the cell 750. Let's say you have issues with the groundwater problem. You cannot go 2.7 feet deep. You only can go to 2 feet deep in the sun because of the groundwater. So we go to 2%, 2 feet deep sun. You go up to your 3.5% slope. So you can get a length of the cell somewhere between 500, 750. Let's say about 580 or close to 600 feet. So this way, you know that you can control the length of the cell by evaluating the depth of the sump that you have and the slope that you have based on your design parameter of the landfill. This way, you can maximize the length of the green cell. I've got to wait a minute for the computer to respond. So basically, this is the hybrid design, and this is where the green cell is going to start and end. And we have some tools and charts that can help us in evaluating the design parameters and maximizing the length of the green cell design. After that, we will go to herringbone, which will be typical grading with 3D grading in here rather than two-dimensional grading in there. So basically, this is what we have. And with that, I will turn it over to Belinda to wrap up and give us some more advantages of the green design.
Thank you. So now I'll go into a few of some construction photos we have for cells that we've done. I think mostly through Florida, we've designed some cells like this. These photos show the construction of the sump. And you can see here on the photo on the right where the leachate collection system sump continues, through the cell, at that pipe slope that Abdul was talking about. And then here you see the sandbags holding down anywhere the slope breaks are as they constructed on the liner level and the geocomposite level. Again, as Abdul mentioned, the invert of the sump is located here, right at the same invert as the sump bottom. So there is no drop from the pipe as in the herringbone design. The pipe would sit up on the top of the sump and drop down into the sump. Here, it rises up from the sump, the bottom. So these photos show the leachate collection pipe going into the sump. Typical construction you see, with the perforated pipe going down the line of the sump, with gravel placed around it and below it for some structural stability. Then the geotextile is sewn over the leachate collection pipe and the gravel, and then the protective soil comes in afterwards. You can see in the back coming in here, it'll be placed over the leachate collection sump. These photos show the views of looking down into the sump and up from the sump on the right. The pipe in the center is the leachate collection pipe, the primary leachate collection, with the leachate cleanout coming up in the center in between these two pipes. The two outer pipes are the risers where you would pump out your leachate from the sump. In this photo, you can actually see the leachate detection riser below the primary lining system. And that pipe comes up from this side of the sump over here and access at the top of the berm. To benefits of the green design. So one of the major benefits of this design is the increase in airspace compared to the herringbone design. You lose a lot less structural fill to construct the cells and a lot less fill to construct the berms around the cell, since you can have, a constant elevation berm around this type of design. This design also allows for lower head on the liner. You have a shorter, or the calculation of the head, you can show that is not as high with this design. And then you have your increase in the sump storage capacity that Abdul discussed, as you can see in this photo here. You'll have that. And then as well as the ease in construction, you don't have complicated three-dimensional slopes or a variable elevation berm around it. So it's much easier to construct this type of cell. You have single slopes, coming from the base into the sump. You do have a little bit of variable slope if you do the hybrid design and need the herringbone portion of the higher end of the cell. And then as Abdul shows, you have increase in the pump capacity, or, because of the sump capacity increase, you have less pump cycles. So that extends the life of your leachate pumps, and then you can consider all the financial beneficial impacts of all these advantages. So with that, I'll take any questions.
So it looks like we got one in the chat here, so I'll go ahead and read it. It says, do you see any differences in the amount of leachate biogeochemical deposit in the LCS between the two designs?
Well, I think that question, I don't know who asked, but referred to me, but I really, I don't think so. If the pumps are maintained and pumping the leachate frequently as designed, as long as the cycle is about, if it's 1 hour, 2 hour cycles, it's not going to make much difference. If it sits in the sun for a longer period of time, that will have the potential for precipitate some of the calcium carbonate. And we're talking about days, maybe weeks. So therefore, if it's operating properly, I don't foresee any problem with that. But that's a valid point. If you have stagnant leachate for a long period of time, you have large potential for creating calcium carbonate precipitate. I hope that answered the question.
One more question for you here. Are there any challenges of the green design construction?
Well, I'll leave that to Belinda. I think she designed constructed a few of them. I don't suspect that, but she can.
I think with any construction project, there's challenges to the construction of a job. I don't know if there's any specific to the green design. I think we're trying to simplify the construction there. So you remove some of those complications, but I think with any construction project, there's challenges that always arise, and you address each one and learn from each job that you do. So no, that doesn't answer the question exactly, but I can't identify.
I can add something to that. I think construction-wise, if you're dealing with the green design cell, the grading should be much easier, because you have two-dimensional slope going at 2%, perpendicular to your leachate collection sump. You are not dealing with 3D, three-dimensional grading like herringbone, where you have 2% course slope and 1% of your pipe draining, which you have the longer length of leachate flow coming to your leachate collection system. Now, I think that will make it easier in grading the base grade. It depends on the site topography when you get to the boundary of the cell. If you have, for instance, in Florida, that should be very easy because you don't have a lot of slopes and reliefs. In other area, you may have to do some grading to match up the existing grade and provide that road or perimeter road around the cell. So basically, I think it should be easier to grade the base grade, but the rest of the berms and other stuff is typical of any site that you are developing.
Thank you. Any other questions? All right, with that, we'll hand it over to Stephanie Hill. Thank you.
Great. Thank you, Belinda and Abdul. That was well done. Thank you. I'll take a moment to share my screen here.
We did, Stephanie, while you're sharing there, we did have one more question that just came in. If Belinda and Abdul are still there, while you're getting that ready, Stephanie, it says, do you think the Green Designs grading approach would work if the sump was outside of the landfill with a penetration through the liner?
Well, I think I suspect I know who asked that question because we were thinking about the green design and if it works for penetration outside the cell. The only thing I think we need to evaluate is on the green design, we depending on the head that submerging the pipe for the flow, to push the flow. As it comes to the sump, the pumps will take care of it, evacuate it. Now, if we design a penetration instead of that, then really it is going to be, it needs to be some thought and analysis because if you are penetrating the sump at the invert, that's mean you are not gonna hold that leachate within your sump as designed to provide that volume. So really, it has to be evaluated and see if it can be done or not, because this is a big challenge. The minute you have gravity penetrating the cell, because the invert is going to be at the invert of the sump if you don't want to pump, and that's mean you are not going to be able to really take advantage of your submerged condition that are going to drive your flow into the sump and as you pump it out. So I would say it has to be evaluated in more detail.
Very good. Christine, any more questions or should I begin the next session?
I believe that is it. Go ahead and start, Stephanie.
Great. Thank you, Belinda and Abdul. I trust you all can see my screen now, so I'll go ahead and start here. Good morning. I appreciate you guys joining us today. My name is Stephanie Hill. I'm a licensed professional geologist, and I lead the carbon sequestration and injection well services at SCS Engineers. I've been a hydrologist for about 25 years now, and I joined SCS about a decade ago. A little personal tidbit about myself: for about 2 years now, I've been living and working out of my motorhome. I do not have a traditional home or office, but although I spend a lot of time at my home base in the Fort Myers, Florida area, I also take my work on the road and quite frequently go visit clients and also see our large and very spread out family. So today I'm going to talk a little bit about a very general overview of injection well technologies, focusing on 2 types of industrial wells: those that dispose of residual wastewater from operations and those that are intended to sequester greenhouse gases. By no means is this session meant to make you an expert or answer all your questions about injection well technologies, but really just to provide a quick overview so that you can drum up some questions and we can talk about those later. If at any time during this session you've got some questions and want to hold on to those to the end, we can address those then. Feel free to stick them in the chat as you're thinking about them. If you want me to go back to a certain slide, annotate the slide number that's in the lower right-hand corner, or you can just pipe up and we'll discuss those at the end. So following this session, you'll understand the benefits of using injection well technologies, how they work, and how they're installed. I'll explain a little while why the geology and regulatory support provide a crucial role in where they can be used. And I'll show you 2 real-world case studies, one each from a disposal well and a carbon sequestration well. Let's see, I think I skipped a little bit too quickly. Let's see, I go through all these. Last, I'm going to talk about some considerations for employing injection well technologies, including chemical compatibility to protect an asset, community outreach for education and project interruption minimization, and economic considerations as you figure your disposal cost, especially for wastewater. When properly sited, designed, constructed, and operated, injection wells can be a responsible environmental management option. But first, I'm going to go into what injection wells are and a little bit about the various classes of those injection wells. The EPA defines each well by its class, by its intended use and injection into or below protected drinking water aquifers. Presently, there are 6 classes of injection wells, each with a specific set of regulatory criteria that address everything from wastewater injection for a Class 1, produced water from oil and gas operations for a Class 2 well, solution mining wells, that's Class 3, the now banned hazardous wastewater wells that inject into drinking water aquifers, that's a Class 4 that's no longer permitted, and Class 5 are stormwater wells typically, and Class 6 are carbon sequestration wells. So as I mentioned earlier today, I'm going to talk about the Class 1 disposal wells, or we like to call them deep well injection, and Class 6 wells or carbon sequestration wells. So although these two types of classes are pretty similar in strict regulatory requirement and operation technologies, they're still quite different. They're both used to permanently dispose of materials. Deep well injection has been employed to manage residual wastewater since the 1950s, so there are many permits nationwide. While carbon sequestration has only taken off in the last few years, incentivized by a desire for environmental stewardship and government incentives. Although there are far fewer permits issued for carbon sequestration wells, the number of pending applications is growing each month. The types of industries that use these classes of wells can sometimes overlap. For instance, we have an electric utility client that has a need to dispose of wastewater in a Class 1 well, but they also have a means of capturing their carbon dioxide from their stacks, and so they need a place to sequester their carbon dioxide in a Class 6. So really any industry that generates liquid residuals may benefit from deep well injection, and any industry with voluminous emissions can benefit from carbon sequestration. And although the administrative process to obtain a permit is similar in both types of wells, the timeline can be exaggerated in a carbon sequestration well since there's more stringent numerical modeling requirements, significant demonstration criteria for movement of the carbon dioxide plume underground, and strict steps to ensure environmental justice is addressed. Likewise, since there's a greater effort required for a carbon sequestration well, it shares a much larger price tag, as you can see from this slide. Injection wells are designed to protect drinking water aquifers, and in a few minutes, I'll show you how they do that. In both deep well injection and carbon sequestration projects, permanence creates certainty with operators, regulators, and with communities. Permanent disposal of wastewater means that it doesn't come back up. It's forever isolated from drinking water resources and from surface streams. Permanent sequestration of carbon dioxide means that it can't re-enter the atmosphere. Deep well injection is a residuals management option for industry seeking business certainty. Treatment plants are tightening their belts and acceptance of certain waste streams that impact their UV filtration processes. So they're cutting off streams that contain emerging contaminants of concern. Use of deep well injection can eliminate those fluctuating treatment plant criteria and can represent significant cost savings to hauling wastewater off-site. Carbon sequestration reduces atmospheric emissions, allows high emission generating businesses to compete in global markets, and helps them reach ambitious carbon intensity goals. The EPA has published numerous documents citing deep well injection as a safe and responsible means for disposing liquid waste. This slide shows the cover of 2 such documents. And these advocate for deep well injection to dispose of liquid waste that contain polyfluoroalkyl substances, or you may have heard them referred to as PFAS. So let's talk a little bit about how injection wells work. First, we need to identify whether suitable geologic conditions exist at a facility that have 3 qualities. 1, the injection or sequestration interval. Is it a thick, laterally extensive formation that has permeability or capacity to accept that injected fluid? 2, is there an appropriate confining unit? Is it, is it thick, laterally extensive that will prevent injected fluids from migrating into the protected drinking water aquifers? And 3, is there adequate vertical separation between the base of that protected drinking water aquifer and the top of the confining interval? So we're essentially looking for a confining unit or a cap rock to keep those injected fluids down in the injected interval so they don't have some sort of artificial migration pathway to send that water up to the base of the underground source of drinking water. So injection wells are installed with multiple strings of steel pipes or casing. Think of it as a set of nested toys or a straw within a straw. Each string of steel casing is progressively smaller and it's cemented in place. This method of construction creates a redundant barrier between the injected fluid and the protected drinking water aquifers. Requirements for continuous monitoring and frequent well tests ensure the well maintains integrity. When injection wells are sited in areas with suitable geology, when they're properly designed and installed, and when the monitoring, reporting, and testing plans are properly implemented, then injection wells can be a responsible water management option that effectively protects drinking water aquifers. Deep well injection and carbon sequestration wells are very similar, but one difference is that deep well injection takes liquid fluid, while carbon sequestration can either take liquid fluid or supercritical fluid. And I'll talk about that in just a moment. But first, because I realize it might be a little bit of a foreign concept of how you inject carbon dioxide, here's a cartoon that illustrates capture and sequestration of carbon dioxide. Emissions are captured at their point source before they're emitted into the atmosphere, and then they're conveyed through pipelines to an injection well. The captured carbon dioxide can be injected into void spaces underground within abandoned coal mines, depleted oil and gas reservoirs, or just within deep saline aquifers. But there's 2 main phases in which the carbon dioxide can be injected, and this is where I was talking about a liquid fluid versus a supercritical fluid. The carbon dioxide occurs as a gas naturally, but if we blend it with brine, then we get something we call fizzy water. Fizzy water can be injected into a reservoir, but it takes up a lot of valuable real estate or pore space underground. So if we compress that carbon dioxide at temperature and pressure above its critical point, we get a supercritical carbon dioxide. And see the illustration on the left? It shows everything above that critical point representing a substance that's neither a distinct liquid or a distinct gas. And that's a supercritical fluid. So let's move to the illustration to the right now. By compressing the gas into a supercritical fluid, we effectively reduce the volume of the substance by 98%. And when we inject a supercritical fluid into a formation, we can get a lot more carbon dioxide into a smaller space. So injection wells are installed using large drilling rigs capable of drilling through thick, competent rock and handling the anticipated weight of the steel casing. Through a series of alternating sequences of drilling through rock, setting casing, and cementing the casing in place, 2 things are happening. 1, of course, we're installing the injection well. And 2, we're collecting site-specific data. The data can come in forms of water samples to validate the pretreatment to ensure any sort of chemical compatibility, and rock cores to assess the pore size, so we size our filtration media correctly so we don't plug off the well. And the last form is other geologic data to confirm appropriate set points of our casing within competent rock. Those drilling and completion activities typically take place within about 4 to 6 weeks for each well. Injection wells can be used in many locations across the nation. In order to be appropriately sited, several criteria must be met. SCS compiled information from various public sources and developed an easy-to-view figure to quickly identify appropriate siting areas based on suitable geology and regulatory support. On this figure, you see the green markings here on this map represent studied areas that are considered suitable geology for injection. The red areas on the map are those that look, from my screen, they look to be kind of brown, represent studied areas that may not be considered suitable geology. The hatched states that you see are states where injection or sequestration is not yet permitted at this time. And the numbers represent the number of permitted Class 1 deep well injection systems in that state. With these overlaying layers of data, we can determine relatively quickly whether injection may be identified as a viable option in a particular state. I wanted to make note real quickly that you see down in Florida, the number 302 exists. This data is a couple of years old now. I believe that this came from about 2020, but EPA indicates that of the 800 plus Class 1 injection wells across the nation, more than 300 of those reside in Florida alone. This could be driven, of course, by the appropriate geology that we've got within the state, but also from the recent legislative moves to prohibit ocean outfalls. So in the next 2 slides, I'll present a summary of 2 real-world projects to demonstrate cost and schedule for each, a deep well injection project and a carbon sequestration project. This deep well project right here on this screen is located in Illinois and was completed in 2019. The facility needed a reliable and dedicated injection well to maintain its zero discharge status. Their total investment for the injection well system was just under $7 million and took about 2 years from the time we began studying the site to commencement of operation. They presently inject about 10 million gallons annually, and the system is designed to operate for about 30 years, which is the life of the facility. The payback on their investment was just under 9 months, and their disposal costs are less than a nickel a gallon. So in this carbon sequestration project, it's located along the Gulf Coast, and it's presently ongoing, one of our projects that we're working on with SCS. Our client is constructing a refinery and needed a carbon sink for their carbon dioxide sources from the refinery. The total investment for the injection well system, since it's ongoing, is estimated right now at $30 million and will take about 3 years from start to finish. The injection well interval will accept more than 10 million tons of carbon dioxide over about a 10-year period. And that puts their carbon dioxide storage cost at around $3 a ton. So that's before any sort of federal incentives that are offered through the Inflation Reduction Act of 2022. And although we may not have the leisure of a whole lot of time today to go through that, I'm happy to discuss things like the 45Q incentives, tax credits, and qualification requirements offline if you'd like to contact me. So before I wrap up, I wanted to touch on some considerations when employing either deep well injection or carbon sequestration at a facility. First is chemical compatibility. The photos here were taken at the noted depths in the same well. In the one on the left, you can see the open voids along the well bore through the clear fluid. And for clarity, I'll just indicate the photo on the left, we're actually looking straight down the well. So from a depth of about 3,047 feet, we're looking straight down the well. And if you look around the edges, those are the voids you can see, and that's where the fluid is actually disposed of into the formation. Whereas the photo on the right is just 3 feet shallower in the same well. When we looked at the side view, so now we're no longer looking straight down, we're looking out to the side into one of those voids 3 feet lower than the photo on the left. But when we look at that side view at the wellbore, those same open voids are now filled with something that's biological growth, and it slows the rate at which the fluid enters the formation. This occurred because of the resulting incompatibility of the interface of the injected fluids and the native groundwater in the injection formation. Characterization of influent or the injected fluids is critical to performance of the well and the longevity. Compatibility must be evaluated for pretreatment needs at the early stages of design so that we can avoid this situation. Another consideration is community. People want to know what's going on in their community, and if they only get part of the story, they're going to seek out the information to fill in the gaps. But they don't always necessarily receive the most accurate information, so their perception is their reality. Rather than risking a major schedule setback, consider early engagement with the local community to provide accurate information at the start. And the last consideration I'll touch on today is economics. Understanding the economics of your options impacts your business's bottom line. Recent compilations of actual financial data put deep well injection in the running for significant cost savings for leachate disposal. When you consider a potential elimination of waste streams from a water treatment plant or a lack of real estate for constructed wetlands or lagoons, that places deep well injection as one of the most affordable water management options. So I'll provide a closing here to say that deep well technologies have been through decades of improvement, and they're strictly regulated. With redundant protective design components, continuous monitoring and testing, injection wells are a responsible environmental management option. They're an EPA-supported option for permanent disposal with no residuals to have to manage. And isolating wastewater and carbon dioxide from the water we drink and the air we breathe serves to improve our environment. For businesses, use of injection well technologies provides certainty through elimination of varying water treatment requirements, and they also provide significant cost savings over hauling waste off-site. So with that, I thank you for your time, and I think that we've got some time to answer questions before our break.
All right, feel free to chat your questions into the chat here. We do have one right now. It says, do they use horizontal short radius turn to increase the volume acceptance for each injection well?
I suppose it can be used in some applications. We've predominantly used some vertical installations and really maximized the thickness of an injection interval because it really cuts down on cost and any sort of compromise to integrity of wells. Thanks for that question, Charles. And while there's any other ones coming in, please do take note of my contact information, and I'm happy to answer some offline. I see another came in. Can you please provide the current FDP EP status on permitting Class 1 injection wells? Yeah, so this is something that slides a little bit just in terms of review time. I will say that as an overarching comment, FDEP is very supportive of approving Class 1 injection wells. As you saw from the one slide, the figure, there are numerous Class 1 injection wells that are approved in the state of Florida. They have recently had a changeover in their command. So Joe Haberfeld has retired, and Cindy Fischler is officially directing the underground injection control portion of FDP for UIC permits. They are taking a little longer time, and there appears to be some changing components, as you would expect. I think that every program, regulatory or not, seems to go through evolutions. So I hope that addresses your question. If you have some more specificity, I'm happy to address that.
Stephanie, wow, I could type it, but overall timeline code. So starting a new project, I've now got a leachate problem. Or my POTW just said, okay, now we're cutting you off in 2 months. Like, what's my overall timeline from start to finish? It seems like it's going to take a little while to permit and drill.
Yeah. So it's not realistic to think that we can take care of something, get it permitted, drilled, and commence in operation within that 2-month period. But I would say, getting
Right.
started earlier is of course advisable. So, within that 2-month period, we can get you an alternative disposal method for leachate, to take care of your short-term needs, and go ahead and start fast tracking a long-term desire, a long-term asset, such as an injection well operation.
Right. And how
So
long would that take? Yeah, start to finish, like
yes,
for the
so
injection well.
to start to finish, we could make a real quick fatal flaw analysis within about 2 weeks. We can provide an application within several months, and so I would say to get that approved, you're looking at about a year. You're looking at 18 months, really at the quickest turn, and probably a little over 24 months at a longer turn. And that's from start to actual commencement of injection.
Okay, thank you.
You're very welcome. Thank you, Dan. Steve, I see a question from you indicating, is there any data published available on possible human-induced seismicity from CO2 injection? Oh my goodness, there's so much data published on this. In fact, it's the topic of many debates that I've attended and even participated in, especially on an academic level. So this has been studied for many years. The takeaway on this is that there is evidence that supports that there is human-induced seismicity or earthquakes that are actually occurring because of injection. But a lot of the data also tends to point to the huge volumes of water that are injected from saltwater disposal for Class 2 oil and gas waste wells, and not necessarily from Class 1. So I didn't talk about that today, but I will say just very briefly, the way those are very different is that Class 1 wells are few and far between. So you may have one and not another one for many miles around, whereas Class 2 saltwater disposal wells are really clustered in large groups. And when you have a large buoyancy change, meaning we're pulling a lot of oil and gas out of a reservoir, and then we're turning around and injecting a lot of that salt water back down at a deeper formation, you get almost a bounce or a buoyancy in those underground formations. And that's cited in a lot of these academic studies to support what that injection induced earthquake comes from. So there is a lot of data out there. If you Google it, you may be overwhelmed, but I'm certainly happy to summarize what I've known about that if you'd like to talk. Thanks for your question, Steve.
Welcome back, everyone. So we are going to get right back into the presentations. This is Greg McCarron. I'll let him introduce himself, but he's our national leader and expert in organics management. But I'll let him, without further ado, pass it to you. Thanks, Greg.
Okay, thanks, Dan. And Dan, I assume you can see my screen at this point.
Yeah, looks good.
Okay. Yeah, so again, thanks, Dan, and good morning to everyone. My name is Greg McCarron. I'm a vice president with SCS, and I'm our organics management leader across the company and across the country. I've been with SCS for over 30 years now, and working within solid waste management for my entire career, which is now more than 35 years. As a fun fact to share about myself, I'm a lifelong ice hockey player, but now that I'm well into my 50s, I'm getting a little bit too old to be chasing the YPs around the rink. And in this context, YPs are young players, and so I've kind of semi-retired from hockey. I still play now and then, but my new ice-based sport is curling. So having lots of fun with curling these days over the last 4 years since I've been playing. But into my session here, session 5 is on organics management trends. So this is an overview of what's happening across the country with organics management, and we'll look at a lot of different options that folks can employ, and so we're often tasked with whether it's a city or a county or even a private entity asking us, what are our options to manage organics? How can we handle those other than putting them in the landfill or sending them to a waste energy facility? So we'll talk about the different options, and then I'll also illustrate a lot of those options with photos as we move through the presentation. So first step in any feasibility study, any look at options is to understand what organic materials that you need to manage. And so here's a list of the common materials that are managed outside of a landfill or outside of a waste energy facility. It's everything from yard debris to food scraps, biosolids, and food processing residuals of all kinds. I have a couple of examples in here, specifically related to the sugar industry as well as the poultry industry. And later in this segment, Trent is going to be doing a deeper dive into a specific biosolids project. So I won't be talking too much about biosolids. So most of what I'll talk about here centers on yard debris and food scraps, but as noted, it really depends on your specific situation as to what organic materials you want to look at, and it's not only the type of materials but also the quantity. How much material are you in need of in terms of management? So nationally, there's lots of activity with organics management and specifically diversion of food scraps from disposal. And again, from disposal means from landfills, from waste energy facilities. And the reason for that is largely regulatory driven. There's now 8 states that have some type of diversion regulation, and there's also another 7 or 8 large cities or large counties across the U.S. that have some type of diversion regulation on their own. And as just to give you some sense of what this means, California is probably the biggest one to note, just in terms of their population and their regulation. They've calculated that statewide they need to install about $150 to $300 million worth of capacity to handle organics. Again, this is largely food scraps in this context in the California regulatory scheme. There's also lots of climate change initiatives, and so organics diversion usually factors in quite heavily in what you can do to limit climate change and limit greenhouse gas emissions. And with that, there's also lots of money that's available and becoming available. There's a couple shown here that are really proposed bills at this point in time. Both the Compost Act and the Zero Waste Act were introduced actually a couple of years ago, and they're back on the docket in terms of being introduced, and this is at the federal level. The Farm Bill is also coming up. There's talk about incentives for organics diversion in the Farm Bill. Separately, in the 2 big acts that were passed by President Biden, the Inflation Reduction Act has lots of things on climate action plans, and I believe that will be talked about later in the seminar here today. And again, organics management, organics diversion play a lead role, or can play a lead role in climate action plans that cities and counties may prepare for their sustainability reasons. So, beginning to look now at the options as to what you can do with the organics materials. And again, largely I'm going to focus on the food scrap component, but not to, I don't want to suggest that, the other materials that I listed, can be handled in a similar way, but that's the regulatory emphasis is on food scraps, and that's what's getting a lot of attention these days. So I'll concentrate on that. And so lots of times I'll see in presentations like this, folks will put up the hierarchy on the right-hand side, which is the EPA's food recovery hierarchy. I personally like the one on the left-hand side, which is from ILSR, the Institute for Local Self-Reliance. And I think it's just a lot nicer looking graphically, number one, but also has a lot more specificity relative to composting. So both of them are consistent in that at the top of the hierarchy is things like food waste reduction, food rescue, which includes feeding people as well as animals. But then getting down into the compost realm, there's a lot more levels that are shown in the ILSR hierarchy versus the EPA hierarchy. So, we've actually used that hierarchy, and so I'll present next, again, some of the options that we looked at. The next few slides are actually taken from one of our feasibility studies that we have done for a county. So this is, it's specific and at the same time generic for those that want to look at different options. So going from left to right, starting in the left-hand column, the pink boxes are, your reduction and prevention measures. So that's everything from source reduction at the residential level, as well as source reduction at the business level, and includes food donation. Next, moving over to the right in the yellow boxes, now we're trying to look at options that can be employed at the source. So the best example of this would be home composting. So as opposed to putting your food scraps and yard waste out at the curb for collection, to extent that you have a room at your home, you can readily compost those materials. And that's something that I do. I compost my food scraps from actually not only my home, but also from my office here. I take home the coffee grinds and other fruits and vegetables that folks here at the office put in the office bin. Next up, as we look at, again, feasibility planning and looking at options, are the local options, which are the green boxes. And here we're looking at community compost options, drop-off locations. So I'll touch on a little bit, how we collect these materials, but drop-off locations is one thing that has been employed in many locations, including New York City, which just by way of example has, last I saw, over 200 locations within New York City where you can drop off food scraps that are then processed at compost facilities and other similar type facilities. Lastly, on the right-hand side is, getting more into regional processing. So this is more look at a county level, looking at a kind of a centralized compost facility or a centralized anaerobic digester. So delving further into each of these, first with home composting on the left-hand side, again, ILSR, Institute for Local Self-Reliance, they're really a great resource at the home level and the community level. This is a pamphlet that's shown on the left-hand side of my screen is what's called Yes in My Backyard, which is obviously a pun on NIMBYism. And so this is YIMBY, which is promoting again, composting in at one's home or one's backyard. Just by way of example, the notation at the bottom of the screen for this county feasibility study that we did, one of our recommendations was, hey, why don't you provide a $75 subsidy to each household so they can go out and buy kitchen top bins, as well as perhaps equipment that would go out in their backyard and used for home composting. Next up is community-based composting. So this is, as the name implies, dealing with something more than just your own personal residence. So the photos here are actually both from New York City. On the left-hand side is the Queens Botanical Garden, and so this was a design that we did for them. And a neat thing about this particular design was at the garden, which is a public garden, the compost facility was designed to be right within the walking spaces of the facility. Unfortunately, there was some economic issues with this in terms of getting funding from New York City Department of Sanitation. So this has not progressed to actual implementation, but it's a neat design just the same. This facility was, I think, the capacity of that could handle about 300 to 400 tons per year of food scraps. On the right-hand side is actually at a St. John's University, also coincidentally in Queens. And so this handles the food scraps from the university itself. And again, by way of example, and at the bottom notation is for the county feasibility study that we did, we suggested that the county provide $5,000 subsidies to community groups if they were going to implement some type of community-based composting program of some sort. Moving on, next option to illustrate is a food scrap drop-off program. So these are fairly popular. They're gaining traction in all kinds of different locations. These are also New York State examples. On the left-hand side is Westchester County, which is down towards New York City. And then on the right-hand side is Tompkins County, which is Ithaca and the home of Cornell University, among other colleges in that region. And so in this case, residents would, during their daily activities, whether they're driving to work or doing errands, could drop off their food scraps at a centralized location. In this case, picture the green bins. You drop your scraps off in those bins. And then on the right-hand side, the neat part about this, one of these types of programs is then you can collect the full bins with a box truck as opposed to, say, a traditional packer truck. And then as you're collecting the full bins, you can drop off an empty one and kind of swap them out as you go down your route. Again, by way of example, the notations at the bottom of the slide is just an example recommendation that we've provided to other counties that, hey, why don't you set up a pilot program and look at, setting up some drop-off locations, say at your transfer station or municipal convenience center, and see how that goes. And so again, just examples for doing that. Next is now, so if some instances, maybe food scrap drop-off locations aren't, handling enough material that you'd want to divert from your waste stream. And so folks are looking at different collection schemes. So that's everything from a separate truck that's being routed around the streets, picking up separate containers with food scraps. And as folks probably know within the industry, anytime you add another collection vehicle or collection route to the system, that can get quite expensive. So, I mean, technically it's possible, but the economics are tricky to work out. So one novel concept that has been employed in a couple locations is to use a food scrap bag collection system. So in this case, residents are given, special bags that are in some instances compostable, in some cases durable, and they put their food scraps in these bags that are usually some type of color-coded bag, whether that's a green bag or other color. And they simply drop those food scrap bags into their regular MSW cart. And once they come to the transfer station or process facility, those bags are sorted out in various ways. And so the food bags are pulled out and sent to say, a compost facility, whereas the MSW goes on to its location. So here's an actual system that's just been built, and it's just about ready to start up. This is in Minnesota, in the Ramsey, Washington counties. And so on the right-hand side is the in-feed. So the mixed material, the carts and the compostable bags, or the food scrap bags, I should say, are dumped and go into one of the two conveyors that are shown here. The grapple hook, which is the orange equipment here in the slide, is just simply picking out big items that we know aren't supposed to be in the waste stream. So that might be, say, a microwave or a television set or something like that. So that's what's happening on the right-hand side. The material does go up those incline conveyors and then goes to the left-hand photo at that elevated location. Is now at this facility. They're using robots actually to identify the bags, and once they see a bag, these robots will be equipped with a grapple hook. They'll pull those bags out and drop them in the green chute that's shown kind of in the lower right-hand side. So really neat, interesting way to get at food scrap diversion without adding an additional truck to the route. So I'm really interested to see how this program plays out as this system starts up literally within the next weeks or months. So now moving off of collection and home and community-based composting, did want to get into more centralized facilities. So looking at, compost technology. So there's everything from turned windrows to aerated static piles to in-vessel or in-building systems. What I like for process and cost efficiencies is actually a hybrid system. I'll show a couple of examples of those. So that's where we're combining an ASP system at the front end and then followed up with a turned windrow system. So in all instances, and before I jump into the actual photos of the facilities, in all instances, there's kind of common goals, common requirements for any kind of compost facilities or anaerobic digestion facility for that matter. So number one, we need to make a high quality, consistent product. Number two, we need to comply with all regulations. So that's typically the big ones are odor and air emissions, as well as water, contact water and stormwater. And then finally, we need to be cost competitive. So as much as folks want to divert organics and food scraps from landfill and waste energy, we really need to be cost competitive because often these evaluations come down to the literal bottom line, and we need to make sure that we're designing and building these facilities to compete with landfill tip fees and waste energy tip fees. So first example, this is a private operation in Massachusetts. It's an open windrow compost facility, mainly handling leaf and yard waste, but we have brought in various kinds of actually food processing residuals to this site and composted them successfully in the open windrows. That's been everything from potato chip waste, so from the Cape Cod Potato Chip Company, as well as various seafood. So everything from squid to crab, and I forget what else we've handled at this site, but it's definitely a viable technology. And what's shown here is the compost turner on the left-hand side. That's actually a piece of equipment that SCS owns. We purchased that actually 10 years ago. So now we've been operating that compost turner, excuse me, at this site and other sites in New England for the past 10 years. Next up is a site actually in Florida. This is handling the sugar industry. And so this is a large site, just opened up early last year. This site that you see in the photo is about 36 acres in total. At the far end, if you can make that out, is their stormwater pond. That's about 9 acres of the 36 acres. So it's a big pond. It's a quarter of the site. But they wanted to have a zero discharge from the site. And so this is completely self-contained in terms of stormwater. They do recycle water back into the process, and they are composting various byproducts from their industry. So that includes leaves, mill mud, and also ash from their boiler. Next up is a covered aerated static pile system. We're again back to Queens. And so I often use this slide in many of my presentations. So for folks who have seen any of my presentations, this slide would be familiar to you. And the neat thing about this is it's on, I think it's less than 1/3 of an acre, and it can handle 1,000 tons of food scraps per year. The other notable things here is that in the background are 2 residential towers that are 6 to 7 stories high. And so you can imagine if this facility was not a good neighbor, if it was generating lots of odors or other issues, that those neighbors certainly would let the local operator know about that. And so this facility, we did the civil site design here, and this is the other notable point is it's underneath the Queensboro Bridge. We did this design, and the construction was done in 2016, 2017. And so it's been operating at this location for 6 to 7 years. And in fact, prior to moving to this particular location on the bridge, it was at another location further up under the bridge. And so it's been in place for close to 10 years, operating successfully with minimal odor and other impacts on the neighborhood. Next up is a larger facility. This is in Prince George's County, Maryland. This is now a 40,000 ton per year covered area static pile system. It's handling that 40,000 tons is both leaf waste as well as food waste. This is using a gore cover technology. As you can see here in the foreground, those are there's 12 bunkers in total, 9 gore cover systems. We designed this facility back in 2018, I believe. So it's been operating for about 5 years or so. Next is a facility that we helped out with some expansion and modifications to it. This is a hybrid system. So this is kind of the system that I like to see. So on the left-hand side of the photo, which is largely cut off, is their ASP system. In the middle of the site is their windrow turning operation. So after the material goes through the ASP process for about 4 weeks, it comes out and goes through the open windrow turning. And then on the right-hand side of the photo is their screening and sales and blending operation. So this is, I can't recall if I mentioned, but this is a site in Vermont, up in the Burlington, Vermont area. This can handle 5,000 tons per year of food scraps. Moving on into some bigger type facilities, just quickly note, this is a facility in Calgary that can accept both source separated organics as well as biosolids. As you can see, most of this is under roof, under cover. So as you can imagine, it has better controls, I guess you could say, but certainly more costly with all that building and roof. So moving along more quickly, we're working on this facility in Delaware. It's in design now, hoping to go to construction either later this year or early next year. This is going to be handling poultry waste in Delaware. So we have an ASP in a building, and we're sending the building air off to the left, which is a biofilter. Final facility shot is a anaerobic digestion facility. This is a construction photo, but this facility is now up and running as of, I believe it was last year. This is in Maryland, and this is kind of a what I would call a merchant facility. So it's taking in various organics and food scraps from the Maryland area and making biogas, and also producing digestate, which is I believe is going off to either composting or land application. Final slide, just wanted to point out that SCS does have pilot test equipment. So, one thing when we come out of a feasibility study, or folks are looking for what to do, one option is to simply do a test and see if say composting is something that you want to get involved with. And so we can set up a test program for anywhere from 2 months to 6 months and test different recipes, different feedstocks, different organic materials that you might have, and you can assess whether this type of operation is for you, or for your community, and to see what goes into this type of operation. So with that, thank you, and open it up for questions at this point in time.
All right, thanks, Greg. In the interest of time, please chat your questions into the chat with Greg, and he will and he can answer those if that works. And then we'll move on to Steve just to kind of make sure we don't get too far off, if that's all right with everybody. All right. So I guess yeah, we could go on to Steve, and please send your questions to Greg in the chat. Thank you.
Okay.
Thanks, Greg.
Yeah, you're welcome.
All right, Steve. Welcome.
Yep. Let me share my slides here. Let's see. All right. Can you guys see my slide okay?
Yep, sure can.
All right. Well, good morning, everybody. Great presentation, Greg. Always learn something about organics when I hear Greg speak. My name is Steve Stewart. I'm project director here at SCS. I've been with the company about 2 years now. I've been in consulting for over 20 years. I actually stepped away and went to work for one of my clients for about 3 years in manufacturing. And so it was there that, responsible for a couple of different departments, gained an interest in sustainability. We were a company that were experiencing, quite a bit of pressures from our customers to be more sustainable. And so that's actually what led me here to SCS. And so a bit on a personal note, I'm kind of a reuse focus. I'll tell you a little bit about an example of that. Maybe you can come up with a better word. I'm not necessarily a minimalist or a repair enthusiast, but I have this lawnmower, this push mower at home. And so, it's interesting, the engines these days that they produce, they're more reliable, they last a lot longer. And but the other parts, they start to fall apart. I've replaced, for example, a safety cable a couple of times. I've also had to put the wheel on more than once that's fallen off. And so it's a pretty big running joke in my family. My wife makes fun of me for not going and purchasing another lawnmower. So if you can come up with a better term for that, please place that in the chat. I'll be happy to use something that's a little bit more appropriate than just reuse focus. So today I'm going to talk to you a little bit about sustainability and what's happening. So this is kind of my version of the sustainability state of the union, if you will. Let's see. So I always like to start out by calibrating us to the definition of what is sustainability. It seems to be a very broadly used term. It continues to drift, actually. And so you've heard terms like people, planet, profit, the 3 Ps, the triple bottom line, things like ESG. And so the answer to all of those is yes, that does fall under sustainability. Mostly what I'm focused on, our team is focused on, is the E part of the ES and G. Although we do certain aspects of the S and G, we are quite fluid. And even the examples that Stephanie gave with the deep well sequestration and even landfill diversion activities like Greg described falls into that category. So why is sustainability important? We work with a lot of businesses, a lot of large and small businesses, manufacturers and other industries. And, with my personal experience working in manufacturing here recently, there's a lot of pressures, and the pressures are coming from different directions. And so if you haven't been under a rock, you've probably heard about the SEC that has proposed guidelines for large publicly listed companies to start disclosing, similar to financial disclosures. There's going to be requirements to disclose sustainability reporting and goals and how that's being measured and monitoring. And so they're trying to apply some bookends to make sure that companies are not greenwashing and that sort of thing. What we've seen too is companies that are based overseas that are in other countries, or those countries have remained in the Paris Agreement and, didn't necessarily pump the brakes on being a part of that like the US did. We've now resumed that. Those companies have continued to plow forward with, establishing goals, coming up with plans to meet those goals, and also have cascaded those to their US-based facilities. And so those are a good deal of the companies that are reaching out to us right now, because the local facilities in a lot of cases are being left to their own, devices to be able to figure out how they're actually going to achieve those goals. What are the projects that they need to identify and then implement to be able to reach these time-based targets, if you will. Of course, there's companies out there too that investors, if you will, that are only focused on green stocks. I was in a conference last week talking to even a private equity firm that's all that they're investing in, are projects that have a green focus to them and are good for the environment. And so, whether companies, even US-based companies that are probably not all on board yet with having a strong sustainability program, if they're not careful, they're going to get left behind. And so there'll be their competitors that are paying attention to this and are moving forward and publishing their sustainability reports and moving the needle, so to speak. It's something to take into consideration. And of course, I think we've all experienced customers are also giving preference to sustainable products. So consumers out there are paying more attention to who they're buying their vehicles from, for example, and even the types of packaging materials are coming in. There's companies out there that are only producing nature-based products, and there's consumers out there that are very loyal and even willing to pay a premium for a lot of these products. And then, of course, employees are also another avenue that are applying pressures to companies to be more sustainable. We've experienced that even here at SCS. I remember starting in the industry and consulting 20-something years ago, and even working on environmental projects that I felt and really are doing good for the environment. Some of the younger professionals coming in, they want to do even more. So we're trying to make sure that we match them up with those types of projects where they, feel like they're really making a difference there. So, one of the things we've seen is a lot of companies are trying to figure out, well, where do we start with sustainability? And so it's a great question. There's a lot of templates out there that you can use, and we've helped companies with using those templates. But, at a grassroots level, it's more about, okay, well, what, depending on what type of business you're in or industry you're in, what is significant to you? So, there's a lot of focus on climate change, obviously, and so greenhouse gases, but there's plenty of companies out there that really don't have what I consider a significant, greenhouse footprint. They have a smaller greenhouse footprint, but maybe they're using some other natural resources like water, for example. And so, rather than starting with, greenhouse gases where it may be less significant than somebody that's utilizing a lot of water, maybe that becomes a priority. There's this process that's called materiality assessment. And so that's going through, each of these pillars and determining what should be significant, what should be a focus, what should be a priority for your company. And then starting to break it down there. Some of the larger companies, the CEOs have come out and, boldly stated, we're going to be net neutral, carbon neutral, whatever the case may be. by whatever certain year. And so in a lot of cases, though, companies haven't really drilled down to get a really strong detailed roadmap on how to get there. So I think this step is very key. Some of the key aspects of developing a sustainability program is, first of all, establish a strong baseline. Make sure that you understand, exactly what your footprint is, whether you're looking at climate change, the greenhouse gases, or if it's water, or if you're producing a lot of waste. And make sure you understand you have some clear measurements on what has taken place in the past. Hopefully it's been a recent year, and make sure that you have somebody validate that as well. For example, I'll get into it in a later slide, but we've had companies that started down this path of implementing projects, but didn't necessarily have their baseline established. So stakeholder engagement is obviously key, whether you're dealing with shareholders, it could be your employees, it could be other departments within your company, it could be the community around you. And so if you have significant emissions or discharges, you definitely want to engage the community. I've even seen some of the environmental NGOs being engaged in a proactive way. Historically, I think, businesses had a bad reputation of being reactive to NGOs and their concerns. And we've seen a shift in that to be more proactive. Make sure that your goals are clearly established. And then obviously you want to flesh that out in an actual sustainability plan as well. And then what's often overlooked too is benchmarking. So what are other similar companies or businesses or industries and basically your competitors, what are they doing and how are they performing, and some of these metrics that you've taken on as goals to improve upon. And then make sure that the measurements, you're comparing apples to apples, because I think that's one of the challenges these days is that people are measuring things and even in some cases making some calculated estimates as well. And then, how do you plan on reporting that? So, what I've seen is a lot of companies are doing great things out there, but they're not getting credit for it. And I think that's a real shame. And so even if you're not a publicly listed company, you should be producing, if you're going through all of this effort and work, if you will, you need to be getting recognized for that. Think about award programs, recognition programs, have some sort of stakeholder engagement meeting with the community, even talk with media about it. A lot of times companies get a bad rap and they're doing a lot of good things, but they're just not getting the appropriate recognition for that. So a couple of getting down another layer a little bit into the details. Here's a couple of examples of some projects that actually lead to sustainability, because I hear, there's a lot of talk about sustainability, but you may not hear some real specific examples of what companies are doing. In a lot of cases, it's necessary to do some sub-metering to better understand where your consumption, if you've got multiple processes or departments or campuses or whatever the case may be, you have typically your utility meters, I call them out at the street, so to speak, but sometimes you need some internal sub-metering. And there's ways to do that are very, they're not intrusive at all. They're less intrusive and, can even be temporary monitoring and measuring equipment to establish your baseline, or to just periodically check to see how your performance is. Energy audits also is a good activity if you have significant electricity consumption and can, even without metering, for example, there's audits that can be performed to identify energy efficiency measures based on the type of equipment. So looking at the nameplate, the models of the equipment, how it's being operated, there's reasonable estimations of how much energy is being consumed, and to be able to operate that equipment a little more efficiently. One of the low-hanging fruit for a lot of companies, if you have compressed air is a significant electricity consumption activity. In some cases, you can replace that the compressed air compressors with actual blowers, and which are much more energy efficient. I think most people are familiar with solid waste reduction plans, recycling plans, anything related to landfill diversion. Companies are paying attention to that to try to identify ways to either recycle, reuse, or in some cases upcycle. I mentioned a little bit about water stewardship already. We've had companies reach out to us that are significant utilizers of non-potable processed water. And so, similarly to, landfill or recycling, they're trying to reuse water. And so sometimes that only requires, excuse me, a minimum amount of treatment, for example, to reuse that same water multiple times. We've got some manufacturers that reuse the same, I'll call it gallon of water as many as 6 different times before it becomes in a condition where they can't continue to use it, and they have to treat it before they discharge it. Product life cycle assessments, looking at all the inputs to a particular product. If you're in the business of producing or manufacturing widgets of any sort, for example, BASF is looking at, they're kind of an intermediate chemical manufacturer, a very large conglomerate, but they've started looking at their suppliers, and they can even now tell you which plot of land that some of their raw materials or ingredients came from through blockchain tracing, and they know all of these inputs that go into their products and can promote that to their customers. And so you're going to see a lot more technology associated with that, to a point where you'll be able to actually see when you're drinking coffee, where that coffee bean actually came from, and all the inputs to get it to, your cup of coffee that you're enjoying. Carbon credit purchases is of interest as well in the industry right now. We'll talk a bit about that in a second. Quite a few challenges out there that's going on. I mentioned a little bit about making sure your baseline is properly established. I think one of the risks there is if a lot of companies have identified really nice projects that are easy to execute, and so they plow forward executing those projects, but if their baseline's not properly established, they may not be able to get the proper credits for that. And so, for example, in California, they actually have, some caps on GHGs. And so there's more regulatory driven versus voluntary out there in that state. So they actually require a third party validate their greenhouse gases. And so, I think that's the best practice that even us on the eastern side of the U.S. can implement, just to make sure. We actually had a large company recently that we were doing an audit for, and we asked them to look at to be able to look at some of the details of how they calculated their baseline, and actually determined that they were reporting 20% higher than what they actually were. What that means is that they were already trying to determine, capital projects, capital money needs to meet the goals that have been cascaded down to them. If they had held on to that capital and started to implement, that's probably capital they could have used in a more fruitful way somewhere else and within their facility. And so, I think it's an ounce of prevention to get somebody else to validate your greenhouse gases, or whatever your baseline calculation. Scope 3 is the elephant in the room. And so, I've been to some conferences recently, and a lot of the large publicly companies that fall under the SCC requirements, guidelines that are coming out, are really concerned about their suppliers. There's challenges because a lot of times it's going to require renegotiating contracts. It's going to require, basically applying, significant pressure to be more, or the suppliers to be more sustainable, whether that's packaging or the way they're manufacturing or producing their goods, and sometimes even services. There's still a lot of unknowns around some of the clarity of what the SEC is requiring in their disclosure rules. And so, some companies are really jumping out, trying to get a good handle on this. Some companies are kind of holding back a little bit, waiting to see what's going on. And then there's global companies that not only fall under the US and the SEC requirements, but there's some European and some other international disclosure requirements. And so you're going to have some global companies that are having to, send out 3 or 4 different types of disclosure reports for their climate, plans to meet the different formats or requirements of the different standards that are out there. Reporting is still not standardized yet. I think that'll continue to work its way out over the course of maturity. Many companies are waiting to see if the costs will come down on voluntary credits. There's not all credits are equal out there. There's risk associated with some credits versus the others, and companies are trying to navigate through that as well. And there's a lot of green certifications, a lot of reporting software options. With anything new out there, the market's sort of flooded right now. And so I think, the high performers, the better solutions will start to separate themselves from the rest of the pack. And, the appropriate solutions for your company will become, clear as time goes on. But if you had to start today deciding on what software you're going to use, there's going to be a ton of options for you to have to kind of navigate through to find out what's the best fit. I think this has already been mentioned pretty well already. I know Stephanie mentioned it. Greg talked about it. I think we should all be paying attention to the federal funding that's come out that Greg mentioned with the Bipartisan Infrastructure Law and the Inflation Reduction Act. I know a lot of times historically we've thought about grant programs as strictly for public entities. And I think that's still primarily the case with the federal funding that's out there. But there are private companies that are able to take advantage of quite a bit of this. I know one example is anything related to climate change, the GHG reductions, renewable energy. I was talking to a company yesterday that under the same note that Stephanie was talking about, that's investing in a carbon sequestration deep well in South Alabama. Private company just received an award announcement for $23 million from the Department of Energy. And so I'm sure that's going to really help. It was a project that was justifiable even without that funding. So I'm sure they're in a very satisfied position after hearing that award announcement. There's been, other options out there. These are some of the areas that we help in, and we recently added a grant writer to our team to help look at these opportunities. So if you have any questions or feel like there might be something here, or even want to find out more information about funding that's out there, we can assist with that. And with that, I appreciate your time today. If you have any questions, we'll be happy to try to address those. See any questions? So Dan, I'll pass it over to Trent Arney, who'll talk to you a little more about organics and composting. Take it away.
Thank you, Steve. All right, well, you, Trent.
All right, let me get it set up real quick. All right, can everybody see and hear me?
Yes.
Awesome. Hey everyone, my name is Trent. I'm a project professional with SCS Engineers. I've been here for just about 4 years now. I primarily work in solid waste and organics management, and I'm a member of the United States Composting Council, and I'm an active member of the newly formed Florida State Composting Council as well. If you're interested, feel free to reach out to join the Florida State Composting Council. There's my required plug for the presentation. All right, so for those of you who don't know, biosolids are nutrient-rich materials left over after the treatment of domestic wastewater. Nutrient-rich is a very important key word there because it's traditionally viewed as a waste product and a difficult and expensive to dispose of waste product at that. So because it's so nutrient-rich, composting can actually represent a great way to deal with this challenging material. But why? Why should you care about composting? Well, as I mentioned, it can help you to divert the troublesome waste stream of biosolids, but yard waste is another big troublesome waste stream that I know many municipalities struggle to dispose of. Mix the two together and you have a wonderful compost. It can also help you to improve your public image. As Steve was talking about, there's a big push for sustainability in the media and the public lately, and so especially for landfill operators and municipalities. Landfills don't often get the greatest public representation, despite the fact that everybody needs landfills, they don't ever get the greatest public image. And so to add that composting program and that sustainability initiative to your program can really help. Can also help you to support local agriculture. Most of the compost that we produce usually ends up in local agriculture. In this case, in Florida, it's mostly the citrus industry. Can also help you to prepare for potential regulations. Like Greg was talking about earlier, there's a big push for organics diversions and everything. And while we're discussing biosolids in this situation, really any institutional knowledge of composting can help you to prepare for any diversion regulations that may come up. So you have that system and you have that knowledge in place. So now we're going to zoom into Hillsborough County. So we're going to rewind to 2014. They're looking at the population growth curves and they see the writing on the wall. Population is growing rapidly and it's not showing any signs of slowing down. So they need to figure out ways to sustain the current and future population, and also ways to help conserve airspace and save money whenever they can, because they know that this is going to be a challenge in the future. And they were right. Hillsborough County is currently the fastest growing county in the entire state of Florida. So they were right to be concerned. So armed with this knowledge and with this foundation in mind, they started to discuss options. And one of these options that came up was, like I said earlier, we have yard waste, we have biosolids. We can combine the two and make compost. They spent over $2 million trying to dispose of the biosolids, mostly disposed of in landfills. It's very expensive and challenging. So, with that in mind, they decided that they wanted to move forward with a pilot scale test. They wanted a proof of concept. They wanted to be responsible to the taxpayers while trying this new idea. So they started to look at where they could site this new composting facility. They said, hey, we have this landfill cell that we haven't been filling in for a while and we don't plan to fill in the near future. It's a perfect opportunity. So they decided to go ahead and design this pilot scale test to operate on top of the existing landfill cell. This is a great location because you don't have to worry as much about odor control or, public complaints. It's already a property that the county owned, so there was no new leasing, no new siting criteria, and it was already permitted. Well, this was very successful. They completed 2 trial batches, each one totaling about 2,500 tons, and they distributed that to about 1,100 tons to local agriculture. This is a very successful operation, and the county was very pleased. So they decided, let's make it bigger. Let's go ahead and scale up. So they did. Now they scaled it up to a much larger facility that's processing an annual average of over 10,000 tons of biosolids. That produced over 6,200 tons of finished compost. It's a great aerial view of the whole facility and the equipment that they're using. And it's a very successful facility. So let's kind of touch on that equipment a little bit. Some of the composting equipment can be a little specialized. I know Greg mentioned the compost turner. It's a Comtech compost turner. This one is actually owned and operated by the county. and it does exactly what it says it does. It's a little bit of a one-trick pony, and it is absolutely not necessary for a successful composting operation. It exists solely to make the process more efficient and a little bit easier on the operators, but it's absolutely not necessary. You can accomplish a similar effect by using a loader to turn your pile. It might take a little bit longer, but it's absolutely doable. And then another important piece of technology is going to be that compost screener. So what this does is that takes that mixed particle size that you get at the end of a finished compost, and it screens it out to a uniform size that's a lot easier to use for agricultural applications. It's a more desirable product, sells for a higher price, and it's just all around better to go ahead and screen that if you can. And then what you do is you can take the larger particles and you can actually mix them back into your operation and just keep those going. So it's great. Everything was going great, but for those of you who are aware of Florida's climate, the weather, we have what's called a rainy season. It's essentially a monsoon season. And the weather was less than kind to us that summer. The summer of 2016, we got a lot of rainfall. And so we experienced rapid leachate collection and removal issues, ponding issues, and high moisture content. So a compost pile is essentially a giant sponge. It'll absorb almost all the available moisture that it can. So it's just soaking up all of this rainwater. So it leads to a little bit of a less desirable product in some cases and can cause for some operational challenges to overcome. So here you can see one of the operators overcoming one of those challenges. After a heavy rain, that compost, 80% moisture content would start to gum up the screen. And so, they would have to sit out there with a pressure washer and pressure wash it off. So this is one of the reasons that I like to suggest a pilot scale test first is you learn about all of these operational challenges and you learn ways to overcome them. You learn what you do want. And you also learn that in Florida, sometimes it's best to cover it. So with a full-scale facility in 2018, following the enormous success overall of the pilot scale system, they'd approved the new facility at over 3 acres. This would be the largest composting facility in Florida under a single roof. This new facility is capable of processing 30,000 tons of biosolids per year, producing over 12,500 tons of finished product, and all of this product is pre-sold to support local agriculture. I feel like I should mention the process used in this composting because it is not actually one that Greg touched on in his presentation. This one typically will fall in the other category when you're looking at composting methodology. It uses what's called a modified static aerated pile. And what that entails is you do the normal composting windrow and you sprinkle an inoculant on top of the pile. This is contains a lot of healthy active microbes. And what this does is this jump starts that composting process. And the county has had enormous success with that so far. So I wanted to kind of show a before and after because the county is always looking to be as efficient as possible with land use. And so the entire composting facility was actually built on an existing waste tire site. So all the concrete pads you see that they're using for mixing and delivery and curing, those actually already existed and they just retrofitted the existing waste tire site. So some of the improvements that were made for the full-scale facility, as I mentioned, leachate collection can be an issue with composting facilities, especially in the state of Florida. And so there was a whole new leachate collection, drain, and storage tank system to make that a lot easier on them. So now it collects all the leachate that drains through the pad, stores it in the tank so that it can be trucked off as needed. This way, you eliminate the ponding issues and you can help easily control your moisture content in the piles. So this facility is very successful. It's won many awards. It's won the 2021 American Public Works Association Project of the Year Award, 2022 Hillsborough County Planning Commission Outstanding Contribution to the Community Award, which is a bit of a mouthful and makes a terrible acronym. It's also a recipient of the Seal of Testing Assurance. It's a certified compost. This is actually a pretty prestigious program that the United States Composting Council puts on. And that basically just shows that it's a very biologically stable and very nutrient-rich compost. This represents a huge cost savings for Hillsborough County. Saves them over $1.2 million each year. This is just a huge cost savings for any municipality, really, because like I said, biosolids is typically pretty expensive to dispose of. And we could increase this over $2.4 million after the expansion, which, following the trend that you'll notice for this presentation, they liked what was happening, and so they asked SCS to design a new facility. So with the planned expansion, this will nearly double their processing capacity to 55,000 tons per year, producing over 20,000 tons per year of finished product. We did dramatic site regrading, drainage improvements, and we increased the infrastructure available to them. We added a new fuel tank, and we really just wanted to take the design that they had and take everything they had and just really improve it as much as we can to increase the operational efficiency. So due to some rising concerns with biosolids and PFAS, this facility was designed with dual receiving areas if food waste is to be added in the system. We wanted to make it easy to retrofit if needed, so we can make sure we keep that food waste separate from the biosolids. With that in mind, the county did ask us to design a conceptual food waste addition to the proposed expansion. And in doing that, we encountered many challenges in removing the food waste from the waste stream. It was an issue of city versus county ordinances, and then there was complex challenges with collections infrastructure. This is another great reason that we like to recommend a feasibility study, because you definitely will run into these challenges before you start, a full-scale facility. I think some people make the mistake of building their facility and then trying to get, source the material, and sometimes that can represent a pretty large challenge. We did ultimately use this design to apply for the Swiffer grant through the EPA. So this is just a rough look of what we did. So we basically took the last 100 feet of that new expansion building, and we decided to put in a gore-covered aerated static pile technology with the potential to process around 10,000 tons per year, which would produce around 10,000 tons per year of finished product. And the plan was to use this product to support disadvantaged communities. So you've seen the success of Hillsborough County's composting facility, and maybe you're interested in starting your own. So what are some implementation steps? What are some things that you can do to get this process started? Well, I recommend kind of reaching out to your local regulators, local food waste producers, and kind of just assess your collection potential. See what kind of issues that you might run into when you're looking at ordinances, collections, and infrastructure. Reach out to members of the United States Composting Council, including local USCC chapters, as well as other state groups. It's a wealth of knowledge. These people are very knowledgeable. They've been in the industry for quite a long time, and they'd be happy to point you in the right direction. We're always happy to see new people join. Conduct a pilot scale test or feasibility study. Like I said before, it's very important that you start small and slowly scale your production to match your feedstocks and market. The most successful composting facility, if you're producing this just amazing compost, it's going to fail if nobody is there to buy it. So it's very important to do the pilot scale test to kind of get a feel for your market. And like Greg mentioned, we'd be happy to assist you with a pilot test or a feasibility study if you're interested. So feel free to reach out to any of us, and we'd be happy to get you started. So it's time to talk about the elephant in the room, PFAS. It's on everyone's mind, everyone's talking about it, and everyone's concerned about it, and rightfully so. As of April 20th, 2022, Maine did become the first state to ban the land application of biosolids due to PFAS concerns, and that included compost. This was done out of an abundance of caution, and to my knowledge, no other state has followed suit yet, but some may. I'm not super concerned with it hitting the Southeast in the near future, but it very well may. And in fact, it can even happen on a municipality level as well. I mean, just particular county municipalities may decide to ban the application of biosolids, out of an abundance of concern, because extensive testing has not yet been performed on the PFAS content in biosolids and how much of that leaches into the soil. With that being said, Hillsborough County has a provisional soil target cleanup level measured in milligrams per kilogram, and the current results for the biosolids compost for Hillsborough County measures in micrograms per kilogram. So we're well below the current regulatory threshold. But with no permanent regulations being established, we don't really know what the future is going to hold. Thank you. I'd be happy to take any questions you may have.
See the one question there, Trent.
Oh,
Where's
no,
the market for the compost? Retail or large fertilizer processing companies, revenue per ton?
So the revenue per ton varies based on your goals. I know that for Hillsborough County in particular, being a municipality, they're not really supposed to post a profit. So they sell wholesale. So it's all pre-sold to a third-party distributor and at I believe 650 per ton. And that doesn't even represent the largest piece of the pie either for their cost savings. It's mostly just a cost savings mechanism for Hillsborough County. So if you were able to post a profit, then you could absolutely increase that cost per ton. Do I see anything else? Let's see. It's sargassum being composted in Florida. I do know that there are people that are looking into that. There's a lot of research being done, especially in South Florida. I'm not as into the sargassum composting, but I know that there's a lot of research projects being done, and I believe there's a bill floating around the House and Congress in Florida to promote that even further. I haven't seen the elephant in the room of PFAS affecting the willingness to fund composting projects yet, but I do think that it's affecting more on the wastewater processing end, and I know that the technology is increasing to remove PFAS. So I think that most of it is happening on the wastewater processing end. Is Hillsborough breaking even on expense and revenue? Yeah, for the most part, they're breaking even on expense and revenue generated. Like I said, it mostly just represents a cost savings for Hillsborough County, and the profit generated covers most of the operational costs. All right, well, if there's no more questions, I will leave it in Tim and Sherwan's capable hands to discuss some liquids management.
Thanks, Trent.
Thanks, Trent. Great presentation. Hello, everyone. My name is Tim Smith. I am a project director here at SCS. I lead the liquids management practice for the Southeast region. When we say liquids management at SCS, we're talking about several things. We're talking about leachate management, treatment, industrial wastewater management treatment, and groundwater treatment. I've been working on liquids management projects for about 25 years now, and have been with SCS for about 5 years, sitting in the Mobile, Alabama office. Excuse me. Liquids management presentation today is going to be on the current state of leachate management, and will be presented by my colleague here in the Southeast region, Dr. Sherwan Singh. Sherwan is a key member of our Southeast liquids management team. I personally work with him on several projects, and he's extremely knowledgeable in leachate area and leachate treatment. He did his doctoral work in leachate treatment, and now has more than 10 years experience, working on leachate management projects. So with that, Sherwan, you want to take it away?
Sure. Thank you, Tim. So as Tim mentioned, I'm Sherwan Singh. I'm a project manager at Atlanta office, and I've been with SCS for over 2 years, and I have about 10 years of professional experience in solid waste industry. So far we have discussed multiple topics related to landfill and solid waste management, and here we are going to discuss another important aspects of landfill's operation, the leachate. At this time, we all know the presence of the PFAS in leachate is one of the key factors in identifying leachate management and treatment strategies. And as Stephanie also provided one good information on deep well injection. But in this presentation, I wanted to take a step back and provide a little bit background and what is the current state of leachate management practice is in our industry. So it's just the outline where I'll be discussing what leachate is, the challenges of current management practices, what are the options we have in terms of leachate management or treatment option for on-site, and what are the factors that we need to select for or be cognizant about for on-site leachate treatment option. Leachate is primarily results from the rainwater percolating through the waste, and a small amount of leachate is also generated when liquid from the liquid that is originally present in the waste during decomposition or during the waste compaction process. We remove the leachate through this leachate collection system and removal system, leachate collection and removal system, and some of the leachate we also remove from gas collection wells. We remove the leachate to protect human health and the environment. That is the primary goal of all the things that we do as an environmental engineer. And the other reasons are to protect landfill slopes, avoid seeps from the slope, to improve gas collection, and to keep the landfill compliant. And that basically protects the human health and environment from the landfill. Current management practices, the most common is the offsite treatment. As you can see in the chart, about 70% of Florida landfills were sending their leachate offsite to wastewater treatment plants. That's a report in 2015. And the pattern is relatively still the same. Leachate is either hauled or pumped through a force main to offsite wastewater treatment plants. And in several cases, the landfills are required to pre-treat the leachate before sending off to these wastewater treatment plants. Then there are on-site treatment. Some landfills have installed on-site leachate treatment options, and there are few more proactive operators. If they don't have on-site leachate treatment options, at least they are inquiring about what are the options that are available for them for on-site treatment. The other option is, management within the landfill, which is like you can do leachate recirculation, or you can solidify leachate and put it back to the landfill. Landfills mostly in the west coast, where there is not much rainfall. In several cases, they are evaporating leachate in the pond or spraying it over the active area. So although offsite treatment is the most common option that we have at the moment, and that's what we are using, it is gradually becoming more and more challenging. And one of the challenges, the hauling, if wastewater treatment plant is not close by to the facility, to the landfill, or landfill and wastewater treatment plant, there is no sewer line in between. Leachate hauling in tanker trucks is a big challenge, and it is costly. Then there are those pre-treatment limits that wastewater treatment plants are setting on key leachate parameters. That's a big challenge. Landfill operators want to be a landfill operator, not a wastewater treatment plant operator. So that's a challenge. Then in some cases, wastewater treatment plants are putting surcharges on key parameters like ammonia, color, BOD and COD, that have potential to impact their overall treatment performance due to the pre-treatment regulations. Then the presence of this per and polyfluoroalkyl substances in leachate, the elephant in the room, and the potential regulations of the biosolids is also causing increasing resistance of accepting leachate at these wastewater treatment plants. There are few landfills that send leachate to local wastewater treatment plants and accept sludge in return. That's another option that is being used. Even in this scenario, sometimes landfills are getting pushed back from wastewater treatment plants due to this potential concern of PFAS. But one of the key things to observe is that the wastewater treatment plants are not necessarily treating the leachate, and the treatment is done primarily through dilution. Still, considering leachate contains refractory organic compounds and ammonia as such in high concentrations than these wastewater treatment plants are designed for, so they often struggle with the treatment effectiveness. Also, swapping leachate, as you see in this chart, in this diagram below, swapping leachate with sludge not necessarily removes much of the liquid from the landfill. And almost every 2,000 tons of sludge roughly contains about 50,000 gallons of leachate. So that's a big challenge for landfill operation as well as in terms of leachate treatment. So because of these reasons, more and more landfills are trying to evaluate on-site leachate treatment options. But if you want to treat the leachate or you want to identify the options for treating the leachate, you want to first find out what you have in the leachate. So typically, leachate is mix of some organic matter, inorganic ions, nutrients, some trace compounds, and that these organic matters are primarily this fatty acids, volatile fatty acids, and some humic and fulvic type compounds. The dark brown color that you see in leachate is mostly because of these humic and fulvic type compounds. They are recalcitrant and harder to degrade biologically, and that's why at the wastewater treatment plants, they are sometimes they ask for color measurement. Then these organic matter are typically measured using BOD, COD, or total organic carbon. Then the other thing leachate contains are these inorganic ions, so some heavy metals, sodium, chloride, and carbonate, sulfates, and you can broadly measure them as the total dissolved solids, hardness, and alkalinity. Nutrients are also present mostly in high concentration ammonia, which is one of the key parameters that wastewater treatment plants look for, and that typically is high concentrations of ammonia are present in leachate. And at the moment, I say if we plan to install a leachate treatment system or planning for even a feasibility of having a leachate treatment system, we need to think about the PFAS and any treatment system that we are trying to install, whether will it be capable of treating PFAS. So now, although we typically know the concentrations of these compounds that I mentioned before in the previous slide, and we can design a treatment system for these compounds, but leachate quality is typically very dynamic and very site specific. So as you see in the chart on the right-hand side, leachate concentration variation with waste age, the pH in the leachate is typically low when at the start of waste filling, and as time passes, it stabilizes to near neutral or little over neutral, like 7.5-ish. And the organic matter also fluctuates. Initial waste degradation process, leachate typically contains high BOD, high COD, meaning it has a lot of biodegradable content and a lot of non-biodegradable content as well. But during methane forming phase, the BOD concentration goes very small, and most of the organic matter that is present is non-biodegradable, that is COD. And the other factors that impact leachate characteristics are, the type of waste that is being disposed of, the climatic conditions, and what operational practices we apply in the landfill. Among all these parameters, waste age is the most critical parameter in determining leachate characteristics and the treatment option that you want to select. So as I mentioned before, this table shows how the leachate characteristics change with the age. And younger leachate, which is between 0 to 5 years, the leachate pH is relatively in acidic form, less than 6 or 6.5. And as it progresses, leachate pH goes around 7.5. other key parameter that I want to show is the ratio of BOD to COD, which is in older leachate, it becomes less than 0.1. That means the biodegradable content is really, really small in the leachate. And that's why these wastewater treatment plants are typically not able to handle the organic matter that we send from landfills through leachate. And that's why I was saying that mostly the treatment is at the wastewater treatment plants, the treatment is mostly because of the dilution, not the treatment as such. And in a typical MSW landfill, ammonia concentrations goes down with age. However, they are still high for biological treatment systems of wastewater treatment plants. Then PFAS, the variation with the age in PFAS is still up in the air, and we are still figuring out where we stand on that. So for on-site treatment, there are several type of treatment technologies have been used for on-site, some are natural processes, some are biological and physicochemical processes. Among the natural processes, the constructed wetlands, phytoremediation, aeration pond, that is one of the kind of pretreatment technology that has pretreatment option that has been used in several landfills. And these processes are typically target they target a contaminant, so they are very compound specific or contaminant specific. But and then there are some biological processes such as activated sludge process, anaerobic digesters, membrane bioreactor. They have been used in landfills. The major issue with these are, they require significant footprint from the landfill. And, landfills, the major business for landfills is to dispose of the waste. And if you take out footprint for the wastewater treatment plant, then that's a challenge. Other on-site treatment technologies are some physicochemical processes, physical and physicochemical processes. Considering leachate contains a significant portion of these refractory organic matter that I was mentioning before, these physical chemical processes are typically more effective for treating or removing those. One of the physical processes are like evaporation and membrane processes. In evaporation, you can use climatic evaporation or thermal evaporation, where landfill gas potentially can be used as a heat source. And but the major challenge with these evaporation processes are that heat requirement that is there, and then sometimes odor and exhaust vapor treatment. Those can be a challenge or need to be think of. The membrane processes, reverse osmosis, have shown a significant promise in removing all type of contaminants, including PFAS. The major advantage with membrane processes are relatively a smaller footprint is required. However, it needs significant energy, and sometimes disposing of concentrate is also a challenge. Among other physical chemical processes such as adsorption, air stripping, chemical oxidation, they have, they are again target specific for compound specific. And like adsorption with activated carbon has shown a significant promise with respect to removing PFAS, but cost is still a factor for that. Other processes, recirculation has been used as a leachate management strategies, to accelerate the waste degradation. However, landfills cannot recirculate leachate forever, and at some point it will have to be removed from the landfill, and especially in the landfill of high precipitation zone such as ours. Deep well injection, Stephanie has touched a lot on it. Several landfills are using, especially in especially in Florida. But site geology is one of the key factor in determining its suitability. And like Stephanie was mentioning, it is one of the more recommended approach for PFAS disposal by EPA. So now in today's day and age, any leachate discussion without specifically discussing about PFAS treatment is incomplete. So wanted to just give a little bit information about what type of treatment technologies are used or has shown promise in removing or treating or reducing PFAS from leachate. PFAS, which is everyone knows, we call forever chemical, present in everywhere and are harder to degrade biologically due to their strong carbon-fluorine bond. And among the treatment process, reverse osmosis and nanofiltration has shown a greater effectiveness in separating out PFAS. And again, as I was mentioning before, the concentrate disposal is a challenge. Deep well injection, that's again one of the most preferred approach at the moment with respect to PFAS, trapping the PFAS in deeper confining layers. Foam fractionation has shown a good effectiveness in separating out PFAS from leachate. But as of now, the information that we have is that mostly they are specific. They target a specific type of PFAS, which are the P4 and P4 type of bigger or long chain PFAS compounds. Those are effectively removed from foam fractionation. So a combination of a reverse osmosis and foam fractionation can be an effective option. Other options such as evaporation, ion exchange, activated carbon are also there, which are effective to some degree for PFAS removal from leachate. So, but overall, the challenges with the on-site treatment are, one is the footprint requirement, especially if you are planning for some biological processes, they may require larger footprint as compared to some physical and physicochemical processes. Then selecting a treatment process is challenging due to site-specific leachate characteristics, and the leachate characteristics are dynamic. So it requires a skilled operator to proactively maintain the treatment system, considering this variable leachate characteristics. And at the moment, it is harder to find skilled operators. So that's another challenge for operating an on-site treatment option. I mean, I was involved with one landfill that had a leachate pretreatment aeration pond, and at some point they had to move on. They could not operate it long term. They had to move out and then moved from hauling leachate to recirculation, and then at the end they settled on a reverse osmosis system. Now, few things to consider when we want to select a treatment process, especially on-site leachate treatment process. What is our current disposal option is, and what kind of future challenges that we see, such as PFAS, or your wastewater treatment plant is saying no, probably I will not be taking the leachate in future. It can be anything. What is then we'll have to see, what is your current volume is, what our expected leachate collection volume will be, what will be the characteristics of leachate, and if we are installing a system at the landfill, what level of treatment I want to establish, what is our discharge criteria, whether I'll be just able to handle the little bit pre-treatment and send it off to wastewater treatment plant. It will be a different criteria that we'll have to select and different treatment process we can select. But at the end, pilot scale evaluation is most recommended before you go ahead and install full scale system. And figure out for the capital and operational cost, because that will vary based on the treatment process we select. So this is a small presentation that I wanted to provide current leachate management practices and challenges that our industry is facing, and what our options are. So with that, if you have any questions, please let me know. You can reach out to me or Tim or anybody in our group. We will be very happy to help you out.
All right. Thanks, Rawan. Yeah, well, they'll chat the questions. So if you guys could just monitor that for the next couple minutes, we're gonna try and stay on track here.
Exactly.
Thank you.
So yeah, let's go. The next presentation, Mr. Daniel Deitch on integrated solid waste planning. Thank you.
Okay. So if y'all can hear me, thank you very much, Rawan and Tim. My name is Daniel Deitch, and I am a vice president with SCS Engineers based in the Miami office, and I've worked as a solid waste planner for more than 30 years. My fun fact is more of a confession. I am a recovering elected official, having served 10 years as mayor of the town of Surfside. So today we're going to talk trash. We're going to talk generally about solid waste planning, some facts and trends, and the basics of solid waste planning. So one of my favorite quotes about solid waste is attributed to William Rathje, may he rest in peace, the renowned garbologist and founder of the Garbage Project. And that quote is that garbage is in sight but out of mind. So as we all know, human activity is increasingly burdening our natural systems and our built environment. And as worldwide population grows, so does the quantity of waste that requires management. So the graphic on the screen is a hierarchy developed by the United States Environmental Protection Agency that helps frame options in terms of the most preferred to the least preferred. Now, of course, the best thing we can do is not create waste in the first place, but I'm not so naive to think that that is easily accomplished. But to effectively manage solid waste beyond developing an integrated solid waste management system is the need and the ability to change human behaviors through thoughtful public policies. And this is where an effective solid waste plan comes into play. So solid waste generation is correlated to the economy and affluence. And as you can see, we've enjoyed both over the last 60 years. So going back to 1960, each person generated on average in the United States, on average, generated a little bit more than 2.5 pounds per person per day. And then fast forward to 2018, the latest data published by the EPA, and we're approaching 5 pounds per capita per day. That is pretty significant. And as you can also see in the graphic presented, there are also some changes in terms of tonnages that are managed by different solid waste management techniques or systems. Now, a key event that I just want to draw your attention to is the first Earth Day, which was celebrated on April 22nd, 1970, which was an inflection point for recycling. It's also interesting to note that waste combustion to produce electricity emerged in the 1980s, largely in response to the oil crisis of the 1970s. So this graphic presents the shifts we're experiencing in the quantities of waste stream components. And while many of the waste stream components have remained relatively stable, food waste and plastics have experienced the greatest increase in tonnage, which is probably not so surprising to you. In terms of markets for the waste stream components or commodities, the once robust global commodity markets are shifting dramatically, and that's having a real impact on municipal recycling programs as well as on their contracted service providers. And most significantly, it's China's national sword policy that was put into place in 2018 that really changed the global markets. When they started to clamp down on the importing of what was essentially contaminated recyclables, a lot of that capacity was picked up by countries in Southeast Asia India, but they quickly realized that they were receiving a lot of waste with the recyclable products. So even those options became less and less available. So this is a very active graphic, but there are a few key takeaways. And mostly that you have to establish an overall context, and there are lots of dimensions that feed into that, from environmental considerations, political considerations, social considerations, cultural, as well as economic considerations. And all of that contributes to what the overall context is that should be considered when developing a solid waste plan. But you can bring resources to bear to help manage through those challenges, which includes external experts, understanding the specific goals of the various stakeholders, analyzing the sources of waste and the types of waste. And now we also have been considering the triple bottom line, which includes both environmental considerations, social considerations, and economic considerations, which I'll touch on in a few minutes. But working through that lens, you can focus on methods to prevent waste, to reduce waste, to recover waste as resources, and ultimately deal with disposal. So I mentioned that there are a lot of policy considerations. I won't enumerate them, but you can see them on the left side of the screen. And as I just mentioned, more recently, a triple bottom line approach has been embraced to frame policy considerations. In terms of profit, organizations mostly depend on financial performance to gauge performance, and profits tend to focus on aspects of a business that generate revenue and also opportunities to reduce costs. This applies equally to private businesses as it does to government. In terms of people, this measures the organization's social impact. It includes the impact to all stakeholders, employees, customers, and the organization's surrounding community, as well as future generations. Methods to help measure this bottom line include advancing human rights, volunteering in the community, promoting diversity, race, and gender equity. And in terms of the planet, this measures an organization's environmental impact, and methods to help measure this bottom line include reducing the carbon footprint by reducing energy consumption and reliance on fossil fuels, improving waste management, and using ethically sourced materials. And as you can imagine, these elements are not absolute and often require trade-offs. So this is a pretty straightforward flow diagram that sort of lays out some of the building blocks of solid waste planning. The first, and I've found this to be a critical success factor, is to establish and charter a steering committee. This can be internal to an organization and also include external resources as well. And then start by conducting baseline planning. You need to know where you are as a starting point for any planning exercise. And as I touched upon a moment ago, assessing policy and institutional framework is critically important, as well as defining the study area characteristics. And then analyzing the integrated solid waste system components that are the as-is condition, both from collection to processing to disposal. And it's important to engage the steering committee and even conduct public workshops so they can start hearing what I consider the voice of the customer, but also start to have public conversations for what could result in significant changes. And at this step, you certainly want to seek input and endorsement from all stakeholders. And then it's important to analyze the integrated solid waste system alternatives, right? So it's important to define what those alternatives might be and evaluate how those alternatives may work and project the system costs. And again, this is another touch point for the steering committee, perhaps convening public workshops where you can seek input and endorsement. From that, you can prepare an implementation plan. Again, another touch point for the steering committee, but you want to identify the elements for implementation. You want to prepare a schedule of capital investment. You want to identify regulatory requirements and then develop an implementation action plan. And once you've done all that, then you can seek policy direction. As I've mentioned a few times, public involvement is critically important, and I would consider this a critical success factor. But it's not sufficient just to check the box. It must be transparent and inclusive. And in terms of transparency, the information sharing must be complete, honest, and straightforward. The interaction should be structured such that each participant contributes value to the process, where it builds trust and cooperation across the stakeholders and facilitates results that best meets the community's needs. It should also be inclusive, right? The impacted stakeholder groups should be represented in the planning process, really because this can minimize friction on the later stages of the planning process when challenges and directional changes can be expensive and disruptive. And as I've also touched upon, the engagement should be frequent, should be routine, and conducted at key decision stages to ensure that stakeholders are heard, and it minimizes corrective actions and rework. Now, just to give a little bit more flavor to establishing a steering committee, it's best to convene one before performing any analysis. It should be large, but not too large. You should secure member commitment, which can also often be facilitated through a chartering session where you can create a common vision, you agree on the operating guidelines, and establish short and long-term goals for that committee. You can also use that time to establish guiding principles, and it can ultimately be memorialized in a chartering document. Okay, so now let's talk about establishing a planning baseline. Again, it's important to start with the current system, identify what works and what doesn't work, and identify opportunities for improvement. But when you're evaluating future needs, it's not sufficient just to consider growth, which is represented on the graphic in the middle. It's even more important to consider where the growth will occur. So the graphics that flank the central chart show in green areas where darker green is higher density. In this case, it's Collier County, where they know where the growth is going to be. It's going to be shifting to the northeast portion of the county, and it's going to be dramatic. So it's important to be planning for the needs of that area. So in terms of integrated solid waste management components, you really need to use a consistent methodology to assess the options, and a broad focus should be utilized. Again, public input is critically important because we all generally understand what we're talking about in terms of technology and approaches, but stakeholders don't. So it's important to include them at every step in the process. So solid waste collection options present some unique considerations in terms of the materials collected, the types of vehicles used, the frequency of collection, and the ultimate disposition of the collected materials. And each of these factors can be addressed in the future to guide customer behaviors to achieve alignment with the system goals. Planners should also consider waste generation from different sources, whether it be residential, multifamily, commercial, and institutional, because each sector does have its own unique challenges and opportunities. The solid waste collection is integrally linked to processing, so available processing options should inform the evaluation of the collection options. For example, if a material recovery facility is being considered to process recyclables, the type of facility matters in terms of how the materials are collected, in terms of single stream or multiple streams. What's most important to remember is that landfills will continue to be an important part of the integrated solid waste management system. So this slide simply presents different technologies that are available. The graphic on the left shows a simple four-box matrix of framing the consideration in terms of potential diversion versus cost or long-term investment. The takeaway from this is that there is no silver bullet. And while there's a lot of talk about emerging technologies from gasification to plasma pyrolysis, they're all interesting and exciting, but please remember that there are no commercially operating facilities in the United States. Therefore, suggest that a greater emphasis should be placed on proven commercially available technologies, but keep your eye on the horizon, especially with those conversion technologies and material processing facilities, as artificial intelligence and machine learning are showing great promise. On the right-hand side is a tool that was developed by Research Triangle International in cooperation with the EPA to evaluate solid waste technologies and solid waste management systems based on a life cycle basis. So it breaks it into the three basic categories of collection, processing, and disposal, and it allows you to run different scenarios to look at what the overall impacts would be. So once you have developed those alternatives, it's important to look at it in terms of capital and operational costs, of the alignment of the alternatives, and other considerations like the required education and training, matters like container screening that do affect quality of life and business operations, extended producer responsibilities becoming more and more important in our business, and as well as the resources required for compliance and monitoring. And I found it's very helpful because when you're projecting out your needs and the approaches to meet those needs in the future, there's a lot of uncertainty. So it helps to look at it in terms of best case, worst case, and most probable scenario. Then it's necessary to have an implementation plan that considers the overall timeline tied to that, the capital investment, the operational commitments, the regulatory approval requirements, the public engagement components, as well as compliance. And then if you're in the municipal context, it's critical. This is the, where the rubber meets the road. You have to tell your story to gain the acceptance of the elected body. So it's important to frame the opportunity, articulate the value, make it actionable, seek policy direction. And this is where that steering committee comes back into play, because they can then become advocates for the process and then also talk about the education and compliance requirements. And that brings us to the short story of a much larger subject of integrated solid waste management planning. So I want to thank everybody for sharing your time with me, and I welcome any questions. I guess it would be best to place it in the chat. And after that, we'll take a 15-minute break and then reconvene. So thank you.
Well, good afternoon, everyone. My name is Bob Curtis. I'm a project director in the Tampa office of SCS. Been at SCS 7 years now. I've got 33 years consulting for solid waste. 20 of those years were in Maine. So one of my interesting facts was Dan had the picture of the cow with the methane gas. And for several summers, I worked milking cows and haying fields. But today we're going to talk about maximizing your landfill airspace. Landfills are a huge enterprise with a lot of things going on each day. A lot of assets, equipment, buildings, machinery, construction materials. But one of the bigger assets is your airspace. And as you consume or fill your landfill, you gain revenue, which is a big asset. Most landfills are older. When you first started designing those landfills 20 or 30 years ago, you met with an engineer and you came up with a plan and you had a design for the landfill. But things change over the 20 years. And so now, there are better ways to manage your landfill with compaction, but also we have new, more precise design tools. So this presentation isn't about designing the landfill or showing you how to design a landfill. It's just showing you some conceptual ideas that we've done in the past or recently to maximize your airspace. And some of those things are, the first one is creating a steeper slope. So, but in order to do this, we as the engineer would look at your slope stability and then revise your operations plan and move on from there with a regulator. Now, before I keep going, a lot of these are conceptual, but also this isn't a game of which landfill is it. So it's not like a Where's Waldo. So the first landfill is in the west coast of Florida. It was designed and permitted in the late 80s. And when they designed it with 4-to-1 side slopes. This photo shows the side slope and kind of generally shows some of the settlement along those side slopes, which we intended to come back and do sliver fills, but then realized we could look at building it out to 3-to-1. Now this is still conceptual, it hasn't been done yet. This is a cross section of the landfill. You can see here, this was the 4-to-1. Then we built it out to 3-to-1. So over 162 acres of this landfill, by going from 4-to-1 to 3-to-1, we would gain about 1.2 million cubic yards, which is about 4 years of life for this landfill. Still conceptual, and again, would have to go through some of the slope stability and stormwater. I will note that this landfill it currently has tack-on berms, as we would for the final closure of this option. The next option to look at would be to eliminate side slope terraces. 30 years ago, when I first started designing landfills, it was normal practice to go up 30 feet. And so every vertical 30 feet, you would have a terrace of 20 feet or so. So you would be designing those terraces in the waste. So in this case, we're going to look at filling in the terraces and putting on tack-on berms. This is another landfill in the west coast of Florida. As you can see, they have 20-foot wide terraces along the sides. These are these white stand out as those terraces. If you look to this side, the terraces aren't as wide. So we looked at this landfill to remove the terraces, fill them in with waste, and put tack-on berms on the closure. I'm going to run through a few more pictures. This one shows another angle of those terraces running along the sides. But in this instance, the landfill operator is limited to the footprint of the landfill because of encroachment by housing or residential areas around them. They can't expand horizontally. So they're looking at filling in the terraces. Here's a cross section. This shows the terraces as you go along. And the more you build in, the more waste you can get as you move up the top of the slope. Initially, these fill areas are going to be like slivers, but then they'll become wider. This is a good point to remember that we have to consider the operational effect of some of these changes as well. So doing this as early as possible to fill in the terraces is important, but also you have to look at how complicated it's going to be and compare that to how much airspace you gain. In this case, this was a 185 acre landfill. They gained about 1 million cubic yards, which is about 5 years of their capacity. Next option would be to piggyback. If you have area beside your landfill, but beside an old subtitle D landfill, you could expand horizontally, installing a new landfill beside it. But in order to gain more airspace, you would then piggyback onto the side of the old landfill. And to do that, you would pretty much just put a geomembrane or a liner system up the side of that slope. This is another landfill, separate landfill, more of central Florida. It's hard to tell, but this green area is where grass or vegetation is already started on the base of the new landfill beside the old one. This is the old landfill, and they put geomembrane up the side to piggyback on this old landfill. Another view trying to capture the horizontal extents. You can see the base liner, then the side slope liner. Something they did on this is they put a rain tarp along that old landfill, along the piggyback portion, to shed clean stormwater so they wouldn't have to treat it as leachate. And as they fill, they remove the rain tarp. Also, I'm going to try to zoom in a little bit. They only went up a certain extent on the old landfill because they knew that if they put the liner all the way to the top, that liner was not going to be covered for a long time, for probably 10 years. And they didn't want to have that exposed to the environment. And they also didn't want the added cost of constructing this additional liner system. Eventually, they will extend the liner up the slope. This is a cross section of that. Here's the old landfill, and then there's the new landfill, and then they piggybacked on with the geomembrane liner system. I don't have the numbers for the volume that they're gaining, but this is actually in practice now. And this landfill is also looked at doing a vertical expansion over the old landfill. So a vertical expansion. Some of the keys there are to make sure that it's politically and publicly accepted to go vertical on your landfill. Again, you have to look at your slope stability, what political pressures you're going to have in the stormwater. I know some landfills are restricted by deed not to go over a certain height, but others have that availability. So for a vertical expansion, this is the older part of the landfill here. And then by going higher, you can put a new liner system on the old landfill, pretty much making this new liner system the subtitle D, and then you go vertically. And here's a cross section. This landfill, for going vertically another 30 feet, will add 900,000 cubic yards or an additional 4 years. Something else to consider is doing horizontal expansions, but by removing infrastructure. Basically, you move the infrastructure to another part of the site and you utilize the space right near your existing landfill. Or you purchase adjacent land or mitigate wetland. The next example I'm going to give is in southern Florida, where it's happening now, or it has been happening. Again, this is the landfill now, and you can see it's a lot of neighborhoods around it, a lot of industrial work, but they've been working to maximize their horizontal footprint. Here's the cells. You can see they've been putting in a lot of cells at this place, but it all started with an unlined landfill. And then they constructed the lined portions or new cells to the south. In the process of doing that, they had to relocate some electrical lines, and then they would then piggyback with a new liner on the old cell. At that time, they've also utilized some deep dynamic compaction of the old waste to gain more space. This shows the crane with the weight to drop and do the deep dynamic compaction. Basically, by doing this, you're compacting the old waste. Given the fact that 30 years ago, the compaction equipment wasn't as efficient or effective. So the same landfill, they then have been moving to expand to the north and to the east. So they purchased two properties, one of which was an auto junkyard, which they removed the junk. And then the second was a lake, which they filled with borrow. They found it more feasible to do these than to find a new landfill. And then they removed some additional electrical power lines and towers along this easement to gain another sliver space. They also relocated buildings and a scale house on the north side to add some new cells, as well as some tanks. And then finally, now they're looking at relocating an existing gas to energy plant. So space is so important and critical that they are going to move this entire plant to some other location in order to have a place to place their waste, an area to place the waste. So by doing this, they had to look at several options. They wanted to maximize the footprint, but they also had to look at the fact that they were concerned about the climate. By not building a new landfill or relocating your landfill, you're not cutting down trees or destroying wildlife, and that's a benefit. The cost would be lower for design and permitting to use the current landfill, as well as the construction cost. You can use the existing leachate collection system, scales, and ponds. There's convenience involved with this as well, that the traffic flow is established. Everybody knows where it's going, so everybody's used to it right now. And then that leads to the NIMBYs, the not in my backyard folks. So you don't have to battle them if you're permitting a new landfill. And again, I had a statement, nobody plans to fail, they just fail to plan, but sometimes you have to adjust as you go along. With that, I'll complete this part of presentation. And are there any questions?
All right.
Okay.
So good, Bob. So good.
Sorry.
There was no questions.
And with that, I will pass it off to Colin and Fove.
Thank you.
Can you guys see my screen?
Yeah, we sure can. Looks good.
Okay. All right. Well, I will start off. My name is Colin Spradlin. I am the landfill team leader here in our Tampa office. I graduated from Auburn in 2011 and have been with SCS for about 6 years. My fun fact is I have a great house sitter. I have a whole menagerie of animals that she watches when we're out of town. We've got 3 dogs, a cat, 2 reef tanks, and about 50 different types of orchids of varying species and hybrids. And I'm here today to present with Fove.
My name's Fove Hearn. I'm a staff professional here in Tampa. I work under Colin. I've been with SCS about 2.5 years now. I graduated in 2020 from the University of Florida. My fun fact, I guess, is not that I have a lot of animals, but I like to travel all around Florida, different hikes, different parks, and just kind of explore what's, in my own backyard. And today we're going to present about site life. So basically, what is site life? I'm not going to spend a whole lot of time going on about what it is, but rather just give a brief overview before we move on to the different calculation methods. So site life is generally determined by density, which is mass over volume. So the volume here would be your aerial surveys, which are usually presented in cubic yards. So they can be done by plane, LiDAR, photogrammetry, any type of methodology, so long as they're done more so on a yearly basis. The mass as part of the density calculation will be provided by the scale receipts, which are generally in tons for the wastes that are entering the landfill. Sorry. Surveys are generally done annually, say August to August or June to June, and the scale receipts are also collected to represent that same time frame. So if you get an August 2021 survey and an August 2022, you'd also have scale receipts that show that same timeline, August to August. With both the survey, the current and previous, you use that to calculate the amount of volume of your landfill that is used. So from there, you can calculate the density of the waste that's entering the landfill because you have your tons and you have your volume. You can combine this with the population of your service area, and therefore you can calculate a waste tonnage per person. And you want to make sure that you are using your service area, not, the closest major city. You want to use what your population that is being serviced by this landfill, whether it's mainly agricultural, a mix of urban and rural. You want to make sure that you're not just focusing on the major city that might be 1 or 2% of your actual service area. And once you have that general annual population, you can extrapolate that along with the tonnages to project out how much waste is going into your landfill year over year until you reach that maximum volume or your site life is 0 and your landfill is officially at capacity. So next, I'll talk about the implications of site life calculations. So why is site life important? First, landfill site life is part of EPA regulations, and it's also included as part of your solid waste permit regulations in many states in the Southeast. the purpose of the calculation of site life is really to determine the financial assurance for a landfill. You want to determine, or a landfill owner operator will determine how much money goes in escrow in order for the landfill to have money for long-term care after volume and has been reached and the landfill is officially closed. Now, these same calcs can also be valuable for the landfill operators to aid in master planning, as well as determination of money for infrastructure improvements outside of this financial assurance cost. So you can use the site life calculations to pre-plan for the future, which includes creating timelines for CIP needs, capital or improvements to the leachate collection, the infrastructure that is part of the landfill. It also can help generate a timeline for expansions, closures, as well as new construction or siting of landfill cells. And all this helps the operators and the owners of the landfill understand the needs of the landfill and prepare themselves for increases in waste, increases in population, rather than being caught blindsided by it. In addition, you can also track the disposal needs of your regional solid waste management system and understand that, you know, if your population's changing, that you can also figure out what needs you need to open a new cell, you need to close a cell, you need to add another scale. It can help with those needs as well. So next I'll discuss the population method for calculating site life. So the population method, aka the traditional method, is generally straightforward. It is based on census or historical population data and economic growth rates within the service area that the landfill is in. Excuse me, sorry. During these calcs, you use data from your service area, again, not just the closest major city. You want to use what represents your service area, industrial, urban, anything. That is what makes up your service area. And from that, you can calculate how much waste and the rate that waste is going into your landfill. So next we'll talk about how to actually calculate the site life. So the population method is dependent on the waste generated per capita, or tons per person within the service area. And that is determined from the population as well as the tons that go over the scale year over year, back to your scale receipts and your surveys you do annually. So this increase in population can be assumed to be linear year over year, with the general average increase, like you see on the screen, of 1.5% year over year. And that's assuming probably your service area has reached capacity, you don't have a lot of new development, a lot of changes going on. But it can also be variable if your population increases, you know, due to urban sprawl, due to development into the agricultural areas, or just a large influx of people like Florida saw after COVID and everything that happened here. So you can also change that to be 2%, 3%, or even if people moved out, you can move it down to 1% or 0.5%. And these changes allow for the solid waste management system to understand how the waste is changing and how they can project out these changes throughout the years until they reach their final capacity. And your annual disposal rate, which I says on here is the 1.5%, can also be changed to represent the service area changes. Again, with the changing population or the changing of type of waste coming in, it might be something that is more food waste, or your service area decides they want to divert food waste, then it changes what kind of comes into the landfill at every time. So next I'll talk about the results of the population method calculations. Yeah. So the results of population method calculations for site life of any type of landfill is based on multiple assumptions. First being that you have to make assumptions on daily operations. This can be your daily compaction rates, your month-over-month compaction rates, or just the monthly density that you're receiving at your landfill. You know, one month you may have more waste that compacts better. You might have another month where you don't have as much waste energy ash or diversions from other landfills. So that leads to the second assumption is that there are a lot of things that can increase your tonnages. So you can have diversions from other regional facilities, say a waste energy plant goes down or a natural disaster hits, and your site is the backup landfill for the one down south that got hit by a hurricane and can no longer accept. It's not something that is routine. You're not going to always receive these diversions, but you might have 1 year where you receive an astronomical amount of diversions or something that is just out of the norm of historically predicted values. So we've seen sometimes where it's 2 or 3 years of site life is lost due to one hurricane that hit where the site had to take in extra debris, extra like items from other landfills all around the region. So you have to assume that all of these things can impact your site life calculations, and allowing them to be brought in allows for a better, accurate representation of how much capacity and how much site life you have left. So the biggest probably assumption is that on population growth rate. That's probably the biggest assumption here for the population method. And that's mainly because population method models your service area population growth. You see here in the slides that population growth can be split into yearly or even 5-year predictions based on historical census data or historical regional data. And this allows you, or allows whoever's calculating this, to project out an estimated growth rate, which, you know, it allows to understand like the waste tonnage per person. And if you're going to increase, you know, 20,000 people in a year, that you understand that your waste is going to go up that much too. But you can also manipulate that to make that faster or slower based on historical projections. If you look and you say, oh, it's 2005 now, you know, jump back in time, but our population's actually increasing at 0.1%. You can adjust that prediction for the future to show that, okay, well, we're not historically average of 0.09, we're actually increasing faster. So then we'll use up more site life faster. And then you can also change it backwards too, if you know your population isn't growing as fast as it was originally predicted by census data or regional data. And ideally, you can see these changes, you know, after, you know, tracking it for a couple of years, and you can extrapolate this out to determine how fast you're filling up over future years or how slow you're filling up, and what changes can be made to better understand where this waste is going and how fast it's being put in there. And so that's ideally what the population-based method is. It's based on population growth and estimates of tonnage assigned to that growth. And now Colin's going to talk about the alternative method to the population-based method. And here you go, Colin.
Hey, thanks, Fove. Yeah, so, you know, that's kind of, as Fove talked about, that's kind of the way I've seen a lot of site life estimates and modeling kind of calculated. And to me, that's kind of the traditional method. I'm sure that there's many other different methods out there. One of the ones that I kind of want to talk to you guys about today is the remaining capacity method. It was actually developed a number of years ago by Bob Stearns, the first S in SCS. And it's basically going to kind of contradictory to the population-based method. It's just going to eliminate population completely. You know, generally as an industry and as, you know, municipalities, the solid waste departments, and as operators, we're not as interested in counting people for the sake of counting people. It's usually with the implication of tying that to some other piece of data, usually being tonnage or volume. And so this method is going to kind of basically consolidate some of those variables and just say, we don't even care about population. What we really care about is the volume consumption trends that we've seen in the past, and then how are we going to project that out into the future and kind of estimate when we're going to consume the volume that is left in the permitted design capacity of the landfill. So what that looks like is basically similar to the traditional method. Of course, we're going to look at an annual tonnage coming into the landfill. This is basically your scale receipts coming across the scales. We're also going to look at historical aerial topography, or whatever type of topography maps you've got, to evaluate on a year-by-year basis how much volume was consumed between two dates, right? We're going to be able to calculate a density based off of your scale receipts, and that's basically going to give us, the annual density we're going to call an airspace utilization factor. So all of these columns over here are going to be on an annual basis, and then we're going to use those year-over-year numbers to also track a cumulative basis for what we've seen over time going into the landfill. And so you can say, Yes, there are years where we have very high densities, perhaps because of operations or the type of waste being taken in. Maybe we're seeing a fluff layer go down into a new cell and then ash going on top of it, or whatever that may be, and we see a lot of settlement that's being accounted for in 1 year. So when we look at the cumulative airspace utilization factor, it helps eliminate some of the variability between years and helps come up with the long-term density number, as well as long-term disposal trends over a number of years. So if we look at it from have a larger set of data, at least 3 to 5 years of annual volume consumption and annual tonnage, it helps alleviate some of that variability that we see in maybe economic upturns, downturns, population growth. And we can certainly, isolate some of those trends if we see that population and disposal rates are increasing with people moving to the area or a change in local industry. We can certainly account for that when we're projecting into the future. So in this particular instance, we take a table and we're going to, in order to make a little bit more of a conservative assumption, we're going to assume that in future years, our density, our achieved density, is 90% of the cumulative density we've seen from 2014 to 2022. That's really just to be conservative. You could go even more conservative. You could say it's 75%. You could say, for planning purposes anyway, we're going to have our new waste to energy plant online, and we think that our densities are actually going to go up in the future, starting in whatever year. And so from there, you can actually add that in and manipulate some of the densities that you believe you will see in each year. You can also, as I was saying, kind of look at the historic disposal of your year to year. And if it is maybe increasing exponentially or a linear increase, or you could take an average, you can use that to kind of project out into the future and what you anticipate your annual tonnage intake to be. So from there, there's a lot of numbers here. As far as visualization of kind of this calculation method, I kind of like to look at the graph. What we're doing is we're taking some of the historical trends and saying, okay, in, let's say 2018, we knew how much volume was left in the landfill based on the 2018 topo map compared to the cut fill analysis of the final build out contours. And we can do that each year all the way out to whatever the current year is. We will use those data points to develop a trend line and basically project that out into the future and use our table for future years to kind of space these red data points along this line until we hit a remaining capacity of 0. Now, if you were to assume that your density in future years is less than historically achieved, you'd end up probably taking in a lesser amount of cumulative tonnage in the same amount of space. If you were to assume that it is a higher density, you're going to be able to fit more tons in the same volume. You're going to end up, further right on this graph where you've got more tonnage in the same amount of volume kind of projected out, and you can see based on this line kind of where those years fall. So as with all models, there's not really one method better than another. The quality of it is really going to depend on the quality of data you put into it. It can be more conservative, less conservative. What we're really trying to do with this model is eliminate a lot of variables. And so as long as your projected future filling and operations you believe to be fairly similar to what they have been in the last 3 to 5 years, we're able to project that into the future. We start adding in other variables, it gets a little bit more complicated and maybe it's a little bit less accurate. As with all models, it's predictive. It's going to get you in the ballpark. I can't tell you today the exact date your landfill is going to close 20 years from now. And I think that there is a reason why they're updated each year in order to kind of track changes as we see on a year-to-year basis. Some of the things that we, I think, make it a little bit easier and help our clients understand the kind of what goes into these is we've seen a lot of bad surveys recently. I think a lot of surveyors are very busy, and it is imperative to get a high quality survey that you can't really do a whole lot with data that is incorrect, like I was saying. And so it's important to turn around those surveys pretty quickly. First thing you want to do is get in there, check your control points, make sure that the hard surfaces look correct, the road elevations didn't change 4 or 5 feet. Anything like that, make sure that the survey is right and get that rectified before we dig into the work. We want to account for stockpiles within the landfill. If there's soil stockpiles or things that we know that are going to be moved and not landfilled, that's pretty easy to take out of the cut fill analysis as long as they're identified at the front end after we receive the aerial survey. We want to account for outside factors, like Fove was saying, waste to energy plants going down, neighboring waste to energy plants going down, a change in service area. Maybe we know that, I don't know, a theme park is going to open back up after a pandemic and there's going to be a lot more waste coming in. Whatever that may be, keep in mind some of the waste trends within your solid waste system that may have an effect on the incoming tonnage. And then, of course, keeping expectations realistic. These are models. We can be pretty accurate with them if we have good data, but it doesn't actually create or lose landfill life. That is going to be a function of how much waste is coming in the future, as well as landfill operations. So we try and do a good job of predicting, and can certainly change the way we're calculating things in order to rectify instances where we think we're not, calculating it appropriately in the past, but it doesn't actually create or lose landfill life. Right? I could talk about site life for a long time. This is basically condensed from an hour and 15 minutes down into 15 or so, maybe 20. So feel free to get in touch with us or shoot us questions in the chat, and I'll be happy to answer them. Next, we've got Stephen and Layla talking about methane mapping.
All right, thank you guys. Yeah, please chat questions to Fove and Colin if you have them. And yeah, Stephen, Layla, who I'm not sure who's going to share, but looks like Layla. Thank you. Welcome. You're muted, Stephen.
All right. All right. So can everyone see the screen? Is on the methane sensing technology slide? All right, perfect. All right, so I think we're the last one, right? So welcome to the final presentation of session 12. You made it. Give yourselves a round of applause, but you can do it muted because we're on a timer, so we got to keep it going. But my name's Stephen Townsend. I've been with SCS for 5 years and work in the landfill gas group out of the Tampa office. Fun fact about myself is I enjoy to play golf and would love to golf with anyone in some upcoming events. So, let me know.
All right. Hey, everybody. My name is Layla Al-Khalaf. I've been with SCS Engineers for about 4-ish years now. I also work with Stephen and the Landfill Gas Group out of the Tampa office. Fun fact about myself is I'm the captain of our SCS kickball team. So, if you're ever interested in participating in a tournament for kickball, let me know.
Yeah, absolutely. All right. So, me and Layla are going to discuss methane sensing technologies and, what we're seeing in our industry currently. We have 3 examples of methane sensing currently being used. We're going to discuss I'll discuss high altitude, and Layla will be discussing low altitude imaging and landfill surface testing. So, just to get into the methane sensing basics, it was originally used for oil and gas, but we're seeing it, pop up in landfill facilities. It provides an increased efficiency due to real-time whole site measurements without the data processing. It gives you the ability to calculate flux for landfills, not just measure concentration. In terms of methodology, they're still in development. There's really no definitive version or regulatory acceptance for some of these methods, specifically high altitude and low altitude testing. Unlike where, you do have some regulatory acceptance for the traditional SEM. Some methods were favored as little as 10 years ago and now are no longer recommended. Layla's going to touch on that later. It's the method 10. Many rely on algorithms that are difficult to verify and calibrate. And, as with anything, each has their pros and cons. So, let's get into high altitude imaging, specifically through satellites and airplanes. So high altitude imaging, you get monitoring through infrared lasers or other spectrum cameras from high altitude devices such as airplanes and satellites. Plumes have been detected and monitored with airplanes and satellites in a limited circumstance. We've provided a couple examples here where we have a satellite image from River Birch landfill in New Orleans in 2021. And to the right, we have NASA satellite image from Aliso Canyon natural gas leak. Just to provide some limitations of high altitude imaging, high altitude technology being used for like regular monitoring events, such as a quarterly SEM, would be far too expensive. At this point, they're primarily a research tool. Smaller, well-controlled landfills may not really even be detectable. And influence of background levels really has not been shown, but that obviously will have some type of influence on your high altitude imaging. To provide some examples of high altitude imaging, NASA Jet Propulsion Laboratory used aircraft methane data to estimate methane emissions. California Air Resources Board is continuing to work through this scientific aviation. The board is also deploying their own methane satellites in the future. Some other examples of high altitude imaging is Carbon Mapper. Carbon Mapper is a company that has set its sights on methane and CO2 mitigation. They've been performing airborne pilot tests, flying over different facilities that have typically high methane or CO2 emissions associated with them. They originally conducted tests in California, but we're starting to see more flyovers in the Southeast United States, specifically Florida, Texas, and I've seen them in Georgia, Alabama, and Mississippi. More of a focus on oil and gas, but landfills are definitely starting to pop up, and we're seeing sites get flown. They're working on comparative studies, comparative message studies using known release rates and detections. And they have plans to launch a constellation of satellites in the next few years. GHG Sat is another company partnered with SpaceX, utilizing satellites for monitoring of greenhouse gases. They launched 3 satellites in 2022, but most of their work has been in open pit coal mines and trona mines. So I want to discuss the difference between ppm and ppm of plume. So basically the data that these high altitude technologies provide. We're used to seeing the typical ppm when speaking about a plume of gas, but these high altitude technologies provide you with a ppm-m data. So this graphic sort of, gives you an idea of how that is determined, right? So it goes from right to left, A to B to C. So you can see at A, we have a plane flying over a point sensor that is giving you 0 ppm, and the laser is not interacting with the plume. So at this point, you would get a reading of 0 ppm-m. At B, you see that there's a plume of gas with a point sensor reading of 15 ppm. That's like the gas concentration, right? So the laser from the plane interacts with this plume at 100 meters. These two numbers are multiplied together, and that gets you your 1500 ppm-m. So I want you to note that even though the plume was only 15 ppm, due to the interaction of the laser at 100 meters, you're getting a reading of 1500 ppm. You can see it's a similar situation, but the plume is getting interacted with at the laser at 30 meters. So even though you have that 15 ppm plume, at 30 meters, you're getting a reading of 450 ppm-m. This graphic's extremely important when discussing and understanding high altitude data, and we want to make sure we're educated on this matter. And so Layla is now going to talk to us about low altitude and drones.
All right, so diving right into the next one, low altitude, which is primarily going to be drones and sniffers. All right, so just to touch on drone and methane sensors themselves, on the left side, you see a typical drone. Depending on the model, of course, it's typically going to have about a 5-mile range, up to about 30 minutes of flight time, and it's going to be able to carry about 3 pounds. So on the right side there, you see that yellow device. That's what's actually going to be measuring your methane itself. So of course the drone doesn't have the capability of doing that. However, when you put those two together, voila, you have low altitude capability imaging. So the device uses the same technology that a high altitude imaging device would. The monitoring involves use of infrared technology, lasers, or other spectrum cameras to actually see the methane emissions from landfills. And the device is going to be a tunable laser diode, and it's tuned only for methane. The detection limit ranges between 1 to 50,000 ppm-m. So again, it's going to be those same units that Stephen just touched on. And what it does is it measures the methane along that column of gas, and the max distance that it does measure is 100 feet. It receives about 10 readings per second, so that's quite a bit of data to handle. So the results are going to be reported as the average of all of those readings. And then on the bottom right there, you can just see an image of our SCS remote monitoring control drone pilots, Melissa and Evelyn. They've been doing some monitoring for emissions in Anchorage, Alaska. All right, so just to get into some limitations of drones, it is an emerging technology. It's not necessarily well demonstrated for landfills just yet. And of course, since it involves the use of a drone, it's going to be a lot more costly when compared to an SCM device that we see on a quarterly basis. However, of course, drones are picking up popularity, so it might get cheaper. This type of imaging technology does show potential for future application and development. However, it is going to take quite some time. A lot of research studies and proposals are going to be needed in order for EPA to use them in regulatory compliance. So to the right here, you can see a methane emission map created from drone imaging. So you can see it's on a gradient scale. So the green in that image map is going to be your lower emissions in ppm-m, and then those yellow and red ones are going to be the higher concentration areas. All right, and just to touch a little bit about other drone capabilities, because it is a very useful technology. Again, it can be used for thermal imagery, high resolution 2D and 3D imagery, topographic mapping that's very popular with surveyors. It can also be used to calculate airspace. can be used to estimate compaction rates, and it is also very useful for infrastructure inspection and analysis. So some of those construction projects that you have going on, if you can't necessarily be on those sites, it's really easy to just go ahead and take a drone, fly over, and now you get a good update on the construction progress. All right, next up we have landfill surface testing, so primarily surface emission monitoring. All right, we're going to go through a couple different options here. So option one, you have a handheld laser. So this is a plume measurement. It uses optical sensors and reflectors to measure the plume density with lasers or infrared technology. It was developed by EPA as that other test method 10. However, it is not really recommended by EPA anymore due to issues with real world technology. So you have those graphics on the bottom there. So the one to the right just kind of provides a good overview of how the device actually works. So you basically have that handheld device. It emits a laser, and that laser is then consumed a little bit by that methane plume, and whatever is reflected back into that device is converted to an electronic signal that carries that information, and it is able to now deduce a methane concentration. All right, second option here for you guys is a flux chamber. So it requires field sampling of methane flux at landfill surface, and the flux is typically measured using chambers that sample a 1 square meter or smaller area of the landfill. So to the right there, you can see an image of the flux chamber setup itself. So that device in the middle is actually that kind of dome-shaped one. That's going to be your actual chamber. And what it does is we go ahead and hook vacuum up to it. And now that vacuum pulls a sample from the landfill. And then we're able to then calculate the methane flux at the landfill surface. So EPA developed this methodology for use primarily in remediation. However, it's not popular anymore. It requires a small landfill, 10 acres or less, and it's just really not popular anymore because better and cheaper options are available. All right, so option 3 here, we have the traditional surface emission monitoring. So this is going to be probably what you guys are most familiar with. It's the most popular method. So EPA method 21, it's the determination of VOC leaks. And what happens is our guys will come out, to landfill every quarter, and they'll use that device to the right of your screen to go ahead and collect samples of surface emissions. And then we'll go ahead and analyze that data, and then we can produce the methane emissions that is coming out of your landfill surface. What we've seen most recently in the past 2 years is now EPA has added another compliance point. So not only are you required to monitor the surface of the landfill itself, but you're also required to monitor penetrations, and penetration just being any kind of object that passes through the landfill itself and touches waste. And of course, just to recap, any reading greater than 500 ppm of methane is an exceedance.
Okay, yeah, just to, summarize the different technologies that we went over, we wanted to provide a table that breaks down the different uses, the pros and cons attached with each technology. Each of the technologies we review today have an application at your site. Ultimately, it's going to be your choice whether which one is really going to work for you. All options are tools you can use to better monitor your facility and provide a greater understanding of the methane at your site. One takeaway from this table is that currently SEM and a modified drone with a sniffer that would fly and simulate your typical SEM route are the only regulator approved methods besides the flux chamber, which is for those smaller sites. All other technologies are used to provide data, but do not have any regulatory repercussions at this time. And finally, it's like, how does this information affect my facility, right? So we wanted to provide more information about technological advances that impact our industry to ensure you are up to date with what's out there. As discussed on the last slide, we want to make sure everyone is aware of what methods are required by rule. We want everyone to be aware of the data that is being provided by high and low altitude technologies, specifically the topic of ppm versus ppm-m. You know, ultimately, our goal is to ensure our clients are being proactive and understanding methane emissions at our facilities and are steadfast in methane mitigation. We feel all of these different technologies all work together to achieve that goal. And with that, please provide any questions in the chat, and thank you for your time.
All right, well done. Are there any questions for, you can raise your hand or put it in the chat. We got a couple minutes before we close things out here. All right, Romana, we owe you a response. Daniel had to not run away, but he had another commitment shortly after his presentation, and so we have communicated with him, and we will get back to you. So apologize for not answering that one promptly, but he had to step away, so we will do that. So I have one last slide that I will share, just my closing slide, which will discuss, I think, that other question that just came across. So yeah, we will be issuing certificates, and we will do that. You know, it's going to be, you know, so I see Robin asked that question. It'll be a few days, Robin. We just got to kind of pull all the data, make sure who is here for what, when, all that, and we will issue the certificates with the CEUs. You know, and then depending upon, you know, if you're a professional engineer and you need those, you'll keep those for your records. We want to thank you, you know, very much for attending. We appreciate it. We appreciate all of you as clients and as partners and trusted advisors, if you will, in this world and working together in this industry. We will send out a survey. I know you get a lot of surveys. We would certainly appreciate any feedback. It is important to us to make sure that, you know, that our topics, that when we do these things are relevant. If there's something you'd like to see more of, you know, you've probably seen 50 PFAS and 50 organics diversion, but at the same time, we include those because they are relevant right now. And then we try to, you know, with the gas one, try to see some emerging technologies, you know, in leachate and then in other areas, so that we kind of give you a well-rounded workshop. So with that, we appreciate it, and we thank you for attending, and we'll end the meeting and the recording. Thank you, everybody.